Using an array of telescopes both on the ground and in orbit, we have found 992 exoplanets. We can now begin to characterize these planets to search for signs of life encoded in the faint light from these distant worlds. One of the best candidates found so far is Kepler 62e, orbiting a star in the constellation Lyra. Identified by the Kepler telescope, this planet appears to have the right size and mass to be a rocky planet. Crucially, it is in the correct orbit to potentially have liquid water on its surface. Remarkably, we are on the verge of being able to look directly into the atmospheres of these planets and search for the telltale fingerprints of life. Demonstration chemical fingerprints. To demonstrate the technique astronomers use to identify chemicals, we can conduct an experiment. We have a selection of 4 different chemical elements dissolved in colourless solution. We will spray them one by one through a Bunsen burner flame. As we spray the first solution, it creates a beautiful green colour. The second solution produces a bright red colour, the science of light signatures. These chemical elements behave differently because of their unique atomic structure. When an element is heated, its electrons jump to different orbits around the nucleus. As they fall back down, they emit light. The specific light or colour we see is determined by the atom's structure. Because each element has a different configuration of electrons, each emits a unique signature of light when heated. This principle is key. Just as elements emit light when heated, they also absorb light of the exact same colours. This property is what allows us to identify elements when they are present in the atmosphere of a star. Alright, let's take that provocative one-line answer. Why are we here? Because we have to be, and open it up carefully, truthfully, and with the sense of wonder it deserves. The idea on the table is eternal inflation, a picture of the cosmos in which the Big Bang is not a one-off event, but a local chapter in a book that keeps writing itself. The essential claim is simple to state and subtle to think about. Our observable universe, everything we can in principle measure with telescopes and particle detectors, could be a single bubble in an immense multiverse, a patch carved out when a peculiar form of energy stopped inflating space here while inflation continued elsewhere. If that's true, then the laws of physics we read off our measurements may be local bylaws rather than universal constitutional law. And if every possible combination of low energy laws and constants is realized somewhere, then regions that look like ours are not merely allowed, they're inevitable. The first thing to say is that eternal inflation is not a whimsical add-on to cosmology. It emerges naturally from the mathematics of inflation itself. Inflation was proposed to explain otherwise puzzling features of our universe, its extraordinary uniformity on large scales, the near flatness of space, and the fact that we don't see exotic relics that many early universe models would have produced. The mechanism is a peculiar energy locked up in a field, a bit like a stretched rubber sheet with potential energy that causes space to expand exponentially fast. When that field relaxes and decays, inflation ends. The stored energy is dumped into ordinary particles and radiation, and a hot Big Bang begins in that region. But here's the twist. In many models, the decay is stochastic random. The field decays here, but not there. So, inflation ends in patches producing bubble universes, while elsewhere the inflating background keeps growing even faster. The part still inflating expands exponentially, outpacing the parts that have finished. That runaway growth means there is always more inflating space left over to spawn new bubbles. That's eternal inflation. Eternal not in time for any one observer, nothing physical lasts forever, but eternal to the future in the global description. New regions keep being born without a final sunset. That picture on its own does not assert that everything that can happen happens. For that stronger statement, we add one more ingredient, that the low energy outcome inside each bubble can differ. Think of the fundamental equations as having many possible ground states valleys in a complicated energy landscape. Different bubbles might roll into different valleys as they cool, each valley defining different particle masses and interaction strength. In some valleys, stars live long and stable lives. In others, chemistry never gets off the ground. The physicist's way of saying everything that can happen happens somewhere is that a sufficiently rich landscape would populate a spectrum of low energy physics across the multiverse. Our particular valley would be one among many. At this point, the question, why are we here, picks up a new layer: selection effects. You and I can only ask the question from regions compatible with our existence. This is not metaphysics, it's logic. If there are many kinds of regions, then observers will be found predominantly in the subset that permits observers. It's the same reason you don't expect to wake up underwater in the middle of the Pacific, not because the planet is waterless, but because beds and bedrooms are a vanishingly small subset of the ocean. In cosmology, we call this anthropic selection. It's not an explanation for everything. It does not replace physics. It says that when a parameter is environmentally selected, when it takes on different values in different regions, the value we observe will be biased toward the observer-friendly range. The cosmological constant, the tiny energy density of the vacuum that accelerates the expansion today, is often presented as a poster child. Theoretically naive estimates predict values vastly larger than observed. If the multiverse realizes a wide spread of values, then only those rare regions where the vacuum energy is small enough will form galaxies before expansion tears matter apart. That doesn't solve the deeper riddle of why there's a landscape at all, but it reframes our measurements. We might live where life can arise, not because the universe was designed for us, but because only such regions contain beings who can take measurements and wonder. Now, there are two essential scientific questions you should press whenever you hear a grand proposal like this. First, is it compatible with what we see? Second, could we ever, even in principle, test it? On the first, eternal inflation is not in conflict with our observations of the cosmic microwave background, the afterglow of the Big Bang, or the web of galaxies mapped by sky surveys. In fact, the small quantum ripples present during inflation seed the very structures we observe, and those statistical fingerprints match well with a very simple picture, nearly scale invariant, almost Gaussian fluctuations with only gentle deviations from perfect scale invariance. If inflation happened, those features are expected. We've seen them. Eternal inflation, however, is an extra layer, a claim about what happens outside our horizon and in other epochs. That's harder. Could we ever catch a whiff of other bubbles? There are speculative suggestions. If another bubble smashed into ours in the very early moments, it might have left a subtle circular blemish in the microwave sky, a faint bruise in the afterglow. People have searched for such signatures, and so far the sky looks impressively featureless aside from the expected primordial ripples and the late-time clutter of our own galaxy. It may be that collisions are rare, or their imprints are too faint, or our bubble's history avoided them. Another avenue flows through gravity's most ethereal messenger, primordial gravitational waves, ripples in space-time generated during inflation. Different inflationary models predict different strengths and spectral shapes for these waves. Experiments that study the polarization of the microwave background, looking for a specific swirly pattern called B modes, aim to detect them. A clear detection would tell us about the energy scale of inflation, which in turn could inform whether the kinds of models that tend to be eternal are favoured or disfavoured. That's not a direct test of other bubbles, but it's how science proceeds. We test the scaffolding piece by piece. There is a deep conceptual challenge at the heart of eternal inflation, called the measure problem. If the multiverse contains infinitely many bubbles and infinitely many observers, how do you define probabilities for what a typical observer sees? Infinity divided by infinity is not a number. It's a request for a precise limiting procedure. Different ways of regulating the infinities, different measures, can yield different answers to otherwise simple questions. Like, what fraction of observers see a particular value of a constant? That's not a trivial nuisance. It's a sign that we don't yet have the final language to describe the global structure. Some researchers argue that the solution will come from quantum gravity. When we properly quantize space-time and understand how to talk about the wave function of the universe, the correct measure will fall out. Others suspect that the entire notion of a global multiverse is the wrong picture, and that we should instead phrase things in terms of what a single observer can, in principle, measure within their horizon. However it resolves the measure problem is an honest, open puzzle, and it's one reason cosmologists are careful when making claims like everything that can happen happens. We mean there are compelling models in which many possibilities are realized, and selection effects then become part of our explanatory toolkit. But we also mean there is work to do to make those statements mathematically sharp. Another subtlety you may have heard about is the spectre of Boltzman brains. If you have an eternally inflating or eternally expanding universe, then exceedingly rare thermal fluctuations might assemble purely by chance, a self-aware observer with fake memories floating for an instant in the void. If that sort of observer vastly outnumbers ordinary observers like us, then typicality arguments go haywire. Most observers would be deluded flickers, not products of a long evolutionary history in a stable environment. This is a reductio test on our models. Any acceptable cosmology should make ordinary observers dominate. That requirement constrains theories of inflation, dark energy, and the ultimate fate of the vacuum. The good news is that many well-behaved models do pass this test. You don't need to believe you're a thermal fluctuation. But the very fact we must check this tells you how seriously cosmologists take the logic of selection and typicality when contemplating the infinite. All this might sound like theorists disappearing into abstraction, but the empirical spine of the story remains firm. Inflation's simplest predictions, the spectrum of primordial fluctuations, the broad geometry of space, the seed structure for galaxies match what we observe. The search for primordial gravitational waves is ongoing. High-precision maps of the microwave background galaxy surveys that measure the clustering of matter over cosmic time and probes of the reionization era and the dark energy-driven acceleration all feed into a tighter picture, the early universe. Even if we never see another bubble's bruise, we can progressively corner the models of inflation that plausibly lead to eternal behavior and those that do not. It is the same scientific attitude that brought us from a hazy, expanding universe to a remarkably detailed standard model of cosmology in just a few decades. Start from simple, testable predictions. Keep what survives the data and be willing to revise the grander narrative if the scaffolding fails. So does eternal inflation answer the question, why are we here? It reframes it. In a single universe picture, the smallness of the cosmological constant or the particular mass of the electron beg for a unique dynamical explanation or a hidden symmetry that fixes those values precisely. In a multiverse, those parameters may be environmental, and the question shifts, why are we in this valley rather than another? The answer becomes because in this valley, stars live long enough, chemistry thrives, and evolution has time to play. It's a long game, so conscious beings can arise to ask the question. That's the sense in which we have to be here, not because we are fated in some mystical way, but because only regions like this contain a we. This is not the end of inquiry. It is perhaps the beginning of a new kind of inquiry where deep dynamical explanations and selection effects sit side by side. We still search for mechanisms, symmetries, dynamics principles that shape the landscape, and we still test the pieces we can reach with our telescopes and detectors. There is one more philosophical point worth airing because it often lurks beneath the surface. Some worry that the multiverse moves physics from explanation to resignation. If everything happens somewhere, why bother? The honest answer is that everything is doing far too much work there. Eternal inflation does not mean every logically imaginable thing occurs. It means that in specific classes of models, a variety of low-energy outcomes are realized, and we must account for selection when we interpret our data. That does not absolve us of the responsibility to find the dynamical story. It challenges us to sharpen it. If a parameter looks environmental, show me the distribution. Show me why the distribution is what it is. Show me the mechanisms that generate it. And show me the falsifiable consequences for the parts of the universe we can see. That's not resignation, that's physics as demanding as ever. And finally, there's the human meaning of all this. Eternal inflation, if true, would say that our observable universe is one luminous droplet in an ocean without shores. For some, that diminishes us. For me, it amplifies the wonder. Our laws, our constants, even our galaxies may be local accidents. But the fact that logic, mathematics, and experiment can reach out from this small world and speak sensibly about the earliest instance and the grandest structures remains one of the finest achievements of our species. We are not here because a cosmic contract required it. We are here because the laws that happen to take root in this bubble made it possible. Our task is to read those laws, test them, and follow them wherever they lead, whether that is to a cosmos of one or a multiverse that forever blossoms. So why are we here in this framework? Because this is the sort of place where here can be inhabited. But the richer answer is that we are here to keep going, to make the quick answer earn its keep, by building theories that predict, by gathering data that constrain, and by keeping our minds elastic enough to hold both humility and ambition at once. If eternal inflation is the right path, it will continue to earn credibility as its scaffolding passes test after test. If it's not, the universe will tell us so and will listen. Either way, the question remains a gift, an invitation to look up, to measure, to imagine, and to understand. Imagine the darkness before any star, before any atom had the chance to arrange itself into something as delicate as a snowflake or as complicated as a brain. Into that quiet, we place a simple question that has animated philosophers and physicists alike: why are we here? The brisk answer offered by a daring idea in modern cosmology is this: because somewhere, somehow we had to be. That idea is called eternal inflation, and it suggests that our universe is one expanding bubble in an ever-growing froth of universes, a multiverse where regions with different local laws of physics constantly bud off and bloom. It sounds extravagant, I know, but it doesn't begin as an extravagance, it begins as a practical fix to real puzzles. and then rather beautifully refuses to stop. Inflation itself is the seed. Picture a field, an energy field, pervading space that for a brief moment behaves like a taut spring. When it's wound tight, its energy doesn't dilute as space expands. Instead, it drives space to expand faster and faster, doubling and redoubling its size in tiny fractions of a second. This is not the ordinary expansion we talk about when we say galaxies are drifting apart with time. This is a furious exponential surge, as if the fabric of space were a film being stretched on a frame. Why introduce such a dramatic chapter? Because it makes sense of three facts our telescopes have been calmly stating for decades. First, on the largest scales we can see, space is astonishingly uniform. The temperature of the cosmic afterglow, the microwave background, differs by only tens of microkelvin across the sky. Second, the geometry of the observable universe is astonishingly flat. Straight lines behave like straight lines even over spans of billions of light years. Third, we don't see relics, magnetic monopoles and other exotica that many pre-inflation models would have left behind in profusion. A brief blast of inflationary stretching explains these. It irons out, wrinkles, dilutes unwanted relics, and makes even a curved space look flat the way any small patch of a sphere feels flat beneath your feet. So far, so reasonable. Now for the twist. In many versions of the mathematics, inflation doesn't stop everywhere at once. The field that drives inflation rolls down an energy landscape. Quantum fluctuations jostle it a little this way and that. In some patches, the field finds a lower energy state, inflation ends, and the stored energy converts into particles and radiation. A localized hot Big Bang begins. In other patches, the field lingers high on the slope and inflation continues. Because inflating regions expand exponentially, they produce more new space than the ending regions can eat up. That imbalance is crucial. It means that even while inflation ends here and there, the total volume still inflating increases without bound. New ending patches keep appearing in an ever-growing inflating background, and each ending patch becomes a bubble universe with its own hot beginning. That's eternal inflation, eternal not to the past, but to the future, a process that keeps spawning new cosmic domains without a final curtain. You can visualize it as a pan of water at a gentle boil. Bubbles form, grow, and separate. The liquid between them continues to simmer and spawns more bubbles. Our observable universe would be the interior of one such bubble, opaque to the others, because the surrounding inflating space accelerates the boundaries away from us faster than any signal can catch up. We are effectively sealed inside our own cosmic weather system, and yet the global story may be a sky filled with countless such weather systems. Now, the multiverse enters not by poetic license, but by a sober observation. The laws we infer inside our bubble, the particle masses, the strengths of forces, even details of symmetry breaking, may depend on which valley of that energy landscape the field rolled into when inflation ended in our patch. In a different patch, the field could settle in a different valley with slightly different local physics. If the landscape is rich, if it offers many valleys, then the eternally inflating process populates many of them. That's when the phrase, "everything that can happen happens," begins to acquire a technical meaning. Not that unicorns are guaranteed, but that wide ranges of low energy constants and particle properties are realized in different cosmic neighborhoods. In that setting, the question, why do the constants have the values we measure, can acquire a pragmatic answer. Because only in a narrow range do long-lived stars, stable chemistry and planetary systems arise. We find ourselves where we can exist. It isn't destiny, it's selection. So when people say eternal inflation answers why are we here with, because we have to be, they mean. Because if there are many possible regions, observers will overwhelmingly be found in the observer-friendly one. That move-invoking selection is not a free pass. It must be used carefully. It matters enormously whether a parameter is truly environmental or fixed by a deeper symmetry. Consider the cosmological constant, the tiny vacuum energy density that causes the universe's expansion to accelerate today. Naive calculations predict values many orders of magnitude larger than observed. If the multiverse samples a wide distribution of vacuum energies, then most regions with large values never form galaxies. Matter races apart too quickly. Only those comparatively rare regions with small vacuum energy produce structures and eventually astronomers. In that sense, the smallness we measure is unsurprising, conditional on our existence. But we must be precise. We need the distribution, not just the story. We need to compute how common different values are, and we need to understand the mechanism that generates that distribution. Here, cosmology bumps into one of its most challenging mathematical thickets, the measure problem. If eternal inflation yields infinitely many bubbles of each type, how do we define how common one outcome is compared to another? Infinity divided by infinity is not a number. It is an invitation to specify a limiting procedure. Different ways of regulating the infinities, different measures, can produce different predictions for the probabilities of observing particular constants. This is not a pedantic footnote. It bears directly on whether the multiverse offers sharp testable statements or dissolves into ambiguity. Ideally, a complete theory of quantum gravity will tell us how to count properly. It may be that the wave function of the universe supplies the correct measure automatically. But we don't have that final word yet. The honest position is to acknowledge the measure problem as an open question and to test the pieces we can reach while we search for firmer mathematical ground. Testing, after all, is the soul of the enterprise. What could we hope to measure from inside a sealed bubble? First, the general inflationary framework makes predictions that do not depend on other bubbles. Quantum fluctuations during inflation get stretched to cosmic scales, seeding the density ripples that later grow into galaxies. Those ripples produce specific statistical patterns in the cosmic microwave background radiation, nearly scale invariant, mostly Gaussian variations, with a slight preference for just a bit more power on larger scale. Satellite missions and ground-based telescopes have mapped those variations with exquisite precision, and the data line up beautifully with expectations from simple inflationary models. Second, inflation can generate a background of primordial gravitational waves ripples in space-time with frequencies set by the energy scale of inflation. Those waves would imprint a faint curly polarization pattern, B modes, in the microwave background. Experiments are pushing hard to detect or bound that signal. Finding it would measure the energy scale of inflation. Not finding it down to a certain level rules out classes of models. Neither outcome directly proves or refutes eternal inflation, but each prunes the tree of possibilities. There are more speculative signatures. If another bubble collided with ours in the earliest moments, the collision might have left a circular blemish, a subtle disc-like modulation in the microwave sky. People have looked, nothing conclusive has turned up. Perhaps collisions are rare, perhaps their marks are too faint, perhaps our patch was spared. Another possibility is that the overall curvature of space might be ever so slightly negative or positive, a fossil of our bubble's birth. Current measurements find space astonishingly flat. Each null result is still a result. It tells us that if eternal inflation is correct, our bubble's history sits in a region of parameter space with few or no dramatic scars. Whenever the conversation turns to eternal, one must also face a curious worry: Boltzman brains. In a universe that lasts long enough, random thermal or quantum fluctuations could, in principle, assemble a self-aware observer with illusory memories, a brain that blinks into being, has a moment of consciousness and dissolves. If such freak observers vastly outnumber ordinary observers that arise after billions of years of cosmic evolution, then typicality arguments go haywire. You and I should expect to be those fleeting, deluded blips, that we are not, our perceptions are coherent, and law-like over time becomes a constraint on acceptable cosmological models. Sensible models of inflation and dark energy avoid this pitfall by ensuring that ordinary observers dominate. It's an excellent example of how an apparently philosophical puzzle turns into a quantitative demand on a theory. There's also the matter of beginnings. Eternal inflation is eternal to the future bubbles keep forming. Is it eternal to the past? There are theorems suggesting that space-times undergoing persistent average expansion are geodesically incomplete to the past. Loosely speaking, that inflationary histories cannot be extended indefinitely backward along every path. That hints that even an eternally budding multiverse likely requires some initial condition or quantum start. Proposals range from quantum tunneling events to no boundary conditions in which the distinction between time and space blurs at the earliest moment. The precise story remains unsettled. But note the pattern. When we press on eternal inflation, it keeps handing us sharp technical questions about measures, about initial conditions, about quantum gravity that a mature theory must answer. At this point, it's worth returning to the human question hiding beneath the physics. Does a multiverse diminish the significance of our world? Some feel that if there are countless other regions, each with its own version of chemistry, or none at all, then our universe becomes just one in a crowd, cosmically ordinary. I don't see it that way. Think about what our measurements mean in such a setting. We live in a region where parameters have settled into values that permit carbon chemistry, planetary systems, and the stability of long-lived stars. Those values are not arbitrary scribbles. They are precise enough to be measured, subtle enough to keep us thinking, and fertile enough to allow life to take root. If there are other regions with other values that does not belittle ours, it contextualizes it. The wonder that we can write equations, build instruments, and read the story of our patch remains undiminished. If anything, the possibility that the cosmos is wider in possibility than our horizon can hold enlarges the canvas on which that wonder is painted. Of course, there is a danger in any grand idea that explains too much too easily. Selection arguments can become a rhetorical blanket thrown over ignorance. The antidote is discipline. Use selection when a parameter is plausibly environmental, compute distributions rather than telling just so tales, derive consequences that can even indirectly be confronted with data. Keep asking whether a deeper symmetry might fix what you are calling environmental. Stay alert to alternatives. Science is not a creed, it's a method. Eternal inflation earns its place not by being imaginative, but by making contact with the parts of itself that can be tested, by surviving those tests, and by guiding us toward the mathematics that will prune or promote it. So here we are near the end of our beginning, with a picture that takes the Big Bang, a once radical idea, and nests it inside a vaster process. Inflation smooths and seeds our cosmos. Eternal inflation suggests the smoothing and seeding go on elsewhere as well. Inside our bubble, the same particles that glitter in detectors at colliders tell a story written in the language of quantum fields and symmetry. On the largest scales, the afterglow of the first light encodes the statistical whispers of fluctuations stretched by that primordial surge. Between those extremes, between particle colliders and microwave telescopes, sits the human project to thread together a coherent narrative out of data and mathematics, to accept uncertainty where it's honest, and to press forward where clarity is possible. And if along the way we find that our universe is a local chapter in a book with many chapters we'll read with the same attention, the same care for detail, the same delight in the plot. We asked, why are we here? The inflationary multiverse offers one kind of answer, because this is the sort of place that can host minds capable of asking the question. That answer doesn't end the conversation, it begins it anew. It sends us back to the sky with better instruments, back to the blackboard with sharper equations, and back to ourselves with a reminder that existence is not granted but achieved by conditions that are in their way, both fragile and magnificent. So we keep going, not because the theory demands it, but because curiosity does. Let's pick up the thread where the mathematics meets the sky, where the boldness of the idea is forced to earn its keep. Inflation, remember, is not an artistic flourish. It is a practical tool that irons the universe smooth and sprinkles it with the tiniest of wrinkles quantum in origin. Those wrinkles, minute variations in density and temperature, are not blemishes, they're the seeds. Left alone for billions of years, helped along by gravity, they grow into stars, galaxies, clusters, and the great filaments that lace the cosmos. If you want a satisfying, testable promise from inflation, that's it. A specific statistical pattern imprinted on the oldest light. We can see the cosmic microwave background, and we've measured that pattern with astonishing precision. It is close to scale invariant, meaning that fluctuations of different sizes have nearly the same strength with just a gentle tilt. It is almost perfectly Gaussian, meaning the random variations behave the way a simple quantum process would suggest, with only tiny room for exotic imprints. That broad agreement is not decoration. It is evidence that a brief early period of accelerated expansion really did happen. Eternal inflation steps in to say that this graceful mechanism carries on elsewhere, that the field which drove the expansion in our patch continued in other regions to hover on the high ground of its energy landscape, keeping those places billowing ever outward while our patch cooled and lit its first stars. You might ask, if those other regions are sealed away by inflating space, what possible hope do we have of inferring their existence? The honest answer is indirectly, cautiously, and with a great deal of humility. We don't look for postcards from neighbouring bubbles. We look for the fingerprints of the inflaton, the field that drove inflation on physics we can reach. That means studying the detailed statistical fingerprints of the microwave background. It means chasing the ghostly swirls of primordial gravitational waves in the polarization of that ancient light. It means mapping the distribution of galaxies across enormous volumes to see whether the patterns agree with the kind of quantum seeds inflation would have planted. Those gravitational waves deserve a moment. They're not like the waves we detect from colliding black holes' thunderclaps in space-time that ring the universe after cataclysm. Primordial gravitational waves would be a faint, broadband hum set down in the first instance, carrying information about the energy scale of inflation. If we find them, we can infer just how high on the energy landscape the universe once perched. Some versions of inflation that tend to be eternal often involve high energy scales, though not all do so. The detection would be a strong nudge toward or away from particular classes of models. If we fail to find them down to vanishingly small levels, we don't refute inflation, we simply rule out the louder variant. That's what progress looks like in frontier physics, narrowing corridors, pruning branches, asking sharper questions, and in that process we often discover that our early intuitions about simplicity, about what should be natural need, updating. The universe is a stern but fair teacher. Another technical thread worth tugging is the distinction between the inflaton and the Higgs field. It's tempting to conflate them because both are scalar fields, fields with magnitude but no direction filling space. The Higgs field is real. It's the field whose non-zero value gives mass to elementary particles like electrons and quarks. But the inflaton in most models is not the Higgs. It's a different field rolling in its own potential with its own dynamics. Could the Higgs have driven inflation in principle under special conditions? But our best understanding of the Higgs potential and the behavior of the early universe suggests that if the Higgs tried to inflate the cosmos, it would run into stability issues or simply not produce the right patterns in the sky. So the conventional picture keeps them distinct. The Higgs shapes the mass and symmetry structure of the low energy world. The inflaton sculpts the earliest expansion and seeds the cosmos. Keeping those roles separate makes the conceptual stage less cluttered and allows each to be constrained by different measurements. Then there is reheating the moment inflation ends in our patch and the inflaton's stored energy is released, not as light bulbs flicking on, but as a torrent of particles and radiation. A hot soup out of which the familiar contents of the universe condense. The details of reheating matter, how quickly the energy is transferred, which particles are produced first, and the temperature reached all leave subtle traces in the relic abundances of light nuclei, in the spectrum of gravitational waves, perhaps even in the small-scale statistics of the microwave background and the distribution of matter. We have a fairly solid handle on what happened a few microseconds after the hot Big Bang began in our patch. The further back we push toward reheating toward the last fractions of a second of inflation, the foggier the view becomes. That's not a weakness, it's a frontier. It tells experimentalists where to point their telescopes and theorists where the mathematics still has room to grow. Eternal inflation as a global story introduces something we're not used to in physics, environmental facts. You and I accept environmental facts all the time in daily life. It rains here, it's dry there, the beach is sandy, the mountain is rocky, but in fundamental physics we've had a taste for uniqueness. There is a single electron mass, a single speed of light, a single set of gauge interactions, a single way the vacuum settles. The multiverse says perhaps not. Perhaps the deep equations, the ones we don't yet fully possess, admit an enormous family of low energy phases and inflation explores them all. If that's true, selection effects become part of sensible explanation. If it's not, then there must be a sharpening symmetry or principle yet to be found that pins the constants where they are and forbids alternatives. Either way, we win because either outcome improves our understanding. So when you hear the phrase anthropic reasoning, don't imagine surrender. Imagine a scientist's hand reaching for a second tool. The first tool is dynamics equations that predict outcomes. The second is selection accounting, for where observers can exist among those outcomes. The art is in knowing when to use which, and in refusing to use selection where dynamics can do the job. Let's wade briefly into the measure problem with fresh eyes. Imagine trying to count how many bubbles of a given type exist in a multiverse that is by construction producing bubbles forever. At any cutoff time there are only finitely many, but as you extend the cutoff further, the counts of all types grow without bound. If different types grow at different rates, your answer depends on how you slide the cutoff forward. That's not a paradox. It's a sign your counting scheme is part of the definition. In physics, when the counting matters, the scheme must come from the theory, not from taste. We learnt this lesson in quantum field theory, where infinities are regulated and renormalized according to rules that preserve the symmetries of the system. A similar maturity may await cosmology, a future quantum description of space-time that tells us how to define probabilities for observations made by observers inside bubbles like ours. Until then, the responsible thing is to explore multiple proposed measures, see how sensitive predictions are to the choice, and watch for any scheme-independent statements, facts that all sensible measures agree on. The mere existence of this problem is a beacon pointing toward quantum gravity. whispering that our current semi-classical language is not yet the final word. One might wonder whether a universe that keeps spawning new regions forever can be eternal to the past as well. The best current theorems indicate no, under broad conditions, space-times with persistent average expansion are geodesically incomplete to the past. Loosely, not every path can be extended indefinitely backward. There must be a boundary, a beginning, or a phase in which our usual notion of time stops being meaningful. That doesn't mean a classical singularity. It may be that near the beginning the geometry becomes quantum. The distinction between before and after softens, and the appropriate question is not what happened earlier, but what state did the universe tunnel from? These are carefully phrased conjectures, not settled facts, but they remind us that even eternal ideas are often eternal in one direction only. The multiverse, if it exists, likely bloomed from something like an initial quantum seed. There is also a delicate empirical symmetry. To appreciate the universe is remarkably flat and uniform on large scales, and yet wildly structured on small ones. Inflation explains the flatness and plants the seeds. Gravity amplifies them. But if inflation went on too long in our patch, or if the seeds were too big, the sky would look different. Galaxies would clump in ways we don't see. The coherence of the microwave background across the sky would fray. At present, the data point to a narrow, happy window, enough inflation to iron out the wrinkles and stretch quantum fluctuations to macroscopic scales, but not so exotic as to spray the sky with flamboyant non-Gaussian patterns. In that sense, our bubble is conservative. It behaves like the simplest stories suggest. And that is precisely what makes the bolder global claims of eternal inflation both tantalizing and hard to test locally. Everything looks disarmingly simple. This brings us to a question that is more poetic than technical, but still matters. Does the multiverse cheapen? Meaning, if there are unimaginably many regions, some very like ours, some profoundly different, does that make our values, our knowledge, our particular sky feel less singular? I don't think so. Meaning is not scarce, it's made. The fact that there could be other valleys on the landscape doesn't drain the wonder from the one we inhabit. In truth, the possibility of a vaster stage enhances the accomplishment of understanding our little part. We have teased out the age of our bubble, traced its expansion history, measured its composition, mapped the afterglow of its first light, and written down exquisitely precise theories that describe the behavior of particles within it. If it turns out that there are other chapters in the cosmic book, that discovery wouldn't turn our chapter into a footnote. It would transform a good story into an epic. And at the human scale, the multiverse, if it is how nature writes, offers a curiously modest answer to grand questions. Why do the constants have the values we measure? Because in other places they do not, and only where they do can questions be asked. Why are we here? Because in a patchwork of possibilities, we inhabit one of the few that allows beings like us to emerge. It's not destiny in the mystical sense, it's inevitability in the statistical sense. That answer will not satisfy everyone, and it shouldn't end the search. The physicist's instinct is to keep asking whether the values we call environmental could in fact be pinned by a deeper principle. Perhaps a future synthesis of quantum gravity, particle physics, and cosmology will sweep away much of the landscape and leave only a handful of valleys, or just one. If that happens, we will gladly trade selection for symmetry. Until then, we use both. So where does this leave us with work to do? With experiments to push forward, models to refine, and mathematical frameworks to test. With an attitude that prizes boldness tempered by evidence, the next generation of microwave telescopes will push deeper into the polarization of the afterglow, stalking the faint signature of primordial gravitational waves. Vast galaxy surveys will sketch the growth of structure with ever more nuance, letting us cross-examine inflation's predictions in the language of clustering and lensing. Theoretical physics will continue to debate the plausibility of landscapes, the constraints from quantum gravity, the subtleties of measures, and the slippery question of initial conditions. Through all of it runs a single thread: we are a species capable of turning curiosity into quantitative knowledge. And perhaps that is the most profound comfort one can take from an idea as expansive as eternal inflation. Even if the universe is vaster in possibility than our horizon can hold, the way we learn remains local, empirical, communal. We point instruments at the sky, we write down equations and test them, we argue, we change our minds, we converge, or at least we narrow. The cosmos, it seems, leaves room for minds to grow within it. So we keep listening for the faintest signals from the earliest moments, not because they guarantee a particular philosophical payoff, but because they are there, and we can. Let's press further into the mechanics, into how a universe like ours might have budded off from a larger, inflating sea, and why that matters for everything from the first atoms to the quiet of the night sky. The picture begins with a false vacuum, which is physics speak for a state that looks stable but isn't the lowest energy resting place. Imagine a ball poised in a shallow dimple on a hillside. From close up, it seems fine. From far away, you notice it could roll into a deeper valley if it can get over a small ridge. In quantum field theory, you don't always need to push. The ball can tunnel through the ridge. Applied to the cosmos, that tunneling is the Coleman-Delucia process. A tiny patch of space decides to be the true vacuum, and a bubble of the new phase appears. Inside the bubble, the field sits closer to its ultimate resting place. Outside space is still in the old inflating state. The bubble walls race outward at nearly the speed of light, and the interior reheats into the particle soup that becomes a hot Big Bang. Our observable universe could be the aftermath of one such nucleation event. The details are technical, but the story is vivid stability that isn't quite stable, a quantum-triggered transition, and a new world forming behind a luminous front. That front, the bubble wall, is not a sheet of metal in space. It's a region where the field changes rapidly. In the thin wall limit, it's like the interface between water and steam, with surface tension and dynamics that can be calculated. In many models, as the bubble grows, the interior stretches so quickly that its curvature becomes negligible, which is why our sky looks so flat. Crucially, if the background outside remains inflating, new bubbles keep appearing elsewhere. You can't go visit them. The space between is growing faster than any signal can traverse. But you can still work out what kinds of bubbles are likely, what their interiors should look like, and how their birth statistics depend on the underlying potential, the shape of the hillside. That's where eternal inflation turns. From a sketch into a research program, classify potentials, compute nucleation. Rates ask what kinds of interiors are common and compare the interiors that resemble ours to observations. At this point, a natural question arises: are there many possible valleys, many low-energy phases with distinct particle physics? In some candidate theories of everything, notably those involving extra dimensions and extended objects, the answer appears to be yes. The effective laws we experience can depend on how extra dimensions are curled up or how fields settle among many minima. That profusion of possibilities is sometimes called a landscape. If inflation samples the landscape, we expect diversity in bubble interiors, different particle masses, force, strengths, and symmetry patterns. That's where selection effects become relevant. We measure what we measure, not because the constants were engraved uniquely into being, but because this combination produces long-lived stars, stable nuclei and chemistry, rich enough to build biochemistry. It is tempting to shrug and say then anything goes, but that is not the right reaction. The right reaction is to ask for structure, what ranges are accessible, how those ranges are populated, and what generic correlations follow, for example, between the amplitude of primordial fluctuations and the abundance of small galaxies, or between reheating temperature and relic particle species. Let's thread this back to the night sky we can actually read. The microwave background, the afterglow from when the first atoms formed, carries a map of density ripples from the infant universe. Those ripples are nearly scale invariant patterns at 1 degree on the sky, have almost the same power as patterns at ½ degree with a slight tilt. The tilt is a clue to the slope of the inflatten's potential, the steepness of the hillside. The ripples are also very close to Gaussian, millions of hot and cold spots whose statistics match what simple quantum fluctuations stretched by expansion would produce. Deviations from Gaussianity, odd shapes in the 3-point or 4-point correlations of the temperature map, are small, which trims back a whole family of wilder inflationary models. This is where the scientific discipline shows the multiverse talk does not shield inflation from tight constraints. If a model predicts too much non-Gaussianity, too much isocurvature, extra flavor in the ripples, or the wrong tilt, it's out. The data don't care for our metaphors. They reward the models that keep their promises. There is another gentle promise: to chase primordial gravitational waves, the hum of space-time, from inflation itself. Detecting that background would be a landmark, because it would point straight to the energy scale of the process. Some classes of models, often those with the field traversing a large distance in its potential, predict a tensor to scalar ratio big enough to be seen by very sensitive polarization measurements of the microwave background. Others predict a signal too feeble to reach with current instruments. Either way, upper limits or a detection prune the tree. And the pruning is cumulative, combined bounds on gravitational waves, with measurements of tilt, with the near absence of isocurvature, with small non-Gaussianity. and the allowed corridors for the potential shape narrow. So even if we never see another bubble, we can learn a great deal about the physics that would make other bubbles likely. It's important to emphasize what eternal inflation does not say. It does not say that anything you can write in a fantasy novel happens somewhere. It does not say physical law is optional. Rather, it says that the deep theory may admit many low energy phases, all consistent with the same high energy principles, and that cosmological dynamics may populate more than one of them. That's bold but precise, and it's the kind of boldness that can be reined in by data. For instance, if future measurements tell us that the inflaton potential must have a particular curvature, or that reheating must have achieved a particular temperature range, whole swathes of the landscape become irrelevant to our history, whether or not they exist in principle. There is a delicate conceptual symmetry to keep in mind. Inflation explains why the universe looks so uniform on large scales, and yet provides the seeds for intricate structure on small scales. That balancing act, smoothness and structure, also underwrites the arrow of time. Inflation takes a messy prehistory, if there was one, and produces a state of low gravitational entropy, smooth, flat, nearly homogeneous. Gravity then amplifies tiny departures into galaxies, stars, and planets, increasing entropy and giving time its familiar direction from order to disorder. If you like, inflation prepares the stage, gravity conducts the drama. The arrow of time is not imposed, it's generated by dynamics that first smooth and then let structure blossom. The fact we live far from thermal equilibrium, fed by the long-lived free energy of starlight, is a consequence of that two-step. What about bubble collisions? Are we sure they left no mark? We're not sure. We've looked for the telltale circles in the microwave sky and found none that pass rigorous statistical tests. That's a non-detection, not a proof of absence. But it already tells us something. Either collisions were rare in our past light cone, their imprints too soft to survive later evolution, or our bubble nucleated and grew in a way that spared our patch a dramatic encounter. Each of those possibilities trims models. In principle, collisions could also generate a spectrum of gravitational waves with a distinctive shape, but disentangling such a signal from later astrophysical backgrounds is hard. Still, the framework invites us to keep looking in clever ways: circles in the sky, peculiar alignments, subtle spectral distortions, even small violations of statistical isotropy. Most such searches will end with nothing found. In frontier work, that's still a form of discovery, a reshaping of the viable space. Let me pivot to a subtle but vital point locality of explanation. Eternal inflation is a global story, but the parts we can test are local. That's not a defect, it's a discipline. Physics has advanced by extracting universal statements from local data. We learned the inverse square law of gravity from the motion of planets and falling apples. We inferred quantum mechanics from spectra and scattering in laboratories. We can do the same with the early universe, use precision observations within our horizon to judge classes of global scenarios. If a global story can never be coaxed into saying anything definite about local observables, then it ceases to be physics and becomes folklore. Eternal inflation, as studied seriously, avoids that trap by flowing through the concrete channels of inflationary perturbations, reheating dynamics and vacuum stability. Stability deserves its own spotlight. Our low-energy world hosts the Higgs field with a particular mass and self-coupling. Extrapolated naively to very high energies, that self-coupling may dip, hinting that our vacuum is metastable, not the absolute bottom of the potential, but a long-lived state. If true, then quantum tunneling to a lower vacuum is possible in principle, though calculations suggest fantastically long lifetimes, far longer than the age of our universe. How does that play with inflation? In many models, the rapid expansion and the presence of large quantum fluctuations could have nudged the Higgs field around in the early moments. Requiring that our vacuum survived places constraints on the inflationary scale and couplings to the Higgs. This is an example of the iterative dance between particle physics and cosmology. What we learn at colliders and in precision measurements informs what's allowed in the early universe. What we infer from the sky feeds back into what kinds of particle models are plausible. There's also the increasingly powerful web of late-time probes, galaxy redshift surveys that chart hundreds of millions of galaxies, weak gravitational lensing maps that trace matter through the way it bends light, measurements of baryon acoustic oscillations, the frozen sound waves from the primordial plasma imprinted in the galaxy distribution. Each of these tools tests how structure grew from the initial seeds. If inflation planted those seeds, then growth should follow a story consistent with general relativity and the measured composition of matter and dark energy. Tensions in growth rates, if found robust, could suggest new physics in gravity or dark sectors, which in turn can reflect backwards on inflationary possibilities. The argument chain can be long, but it is logical. A consistent cosmology ties early and late together. We should also be candid about alternative. There are scenarios that mimic some inflationary successes without invoking a long stage of accelerated expansion, bouncing cosmologies, ekpyrotic models, emergent scenarios. Each faces its own challenges, generating the right spectrum of fluctuations, avoiding instabilities, matching the detailed statistics of the microwave background, embedding the mechanism in a robust high-energy theory. It's healthy for the field to keep such alternatives in play. They sharpen the questions we ask of the data. If an alternative can reproduce the observed statistics and explain flatness and the absence of relics without inflation, it deserves attention. So far, inflation's combination of simplicity and empirical success keeps it the standard, but that status is earned, not decreed. One last theme, because it reaches from equations to ethos humility. Eternal inflation suggests a cosmos in which our observable universe is not the whole story. That can feel destabilizing at first, as if our knowledge were being diluted in an ocean of possibilities. The opposite is true. Knowledge grows precisely because we impose standards on ideas that reach beyond immediate testability. We demand internal mathematical consistency. We demand that every bridge from global picture to local prediction be explicit and checkable. We prune relentlessly when the sky says no, and we keep pluralism without laxity. Several broad pictures may be consistent today. That does not mean anything goes. It means we need better measurements, clever analyses, and often new mathematics. So where next deeper microwave polarization surveys hunting the faint swirls from primordial gravitational waves, larger, cleaner galaxy maps to test the growth of structure and the geometry of space with exquisite precision. Better measurements of neutrino properties, which subtly influence how structures form, and by extension tighten the inferences we draw about the initial ripple. Theoretical advances in quantum gravity that might turn the measure problem from a tangle into a theorem. And along the way, an openness to surprise. The cosmos has a habit of rewarding patience and punishing certainty. The right posture is steady curiosity, neither credulous nor cynical content, to let the data and the mathematics do their slow, magnificent work. If eternal inflation is how nature writes, then we live in a chapter that happens to be gentle, flat, cool old, with stars that live for billions of years and a chemistry that dallies long enough to invent life. If it isn't, then something just as compelling waits to be found. Either way, the task is the same. We keep looking up, we keep calculating, we keep inviting our ideas to fail so that the survivors can be trusted. And in the pauses between results, we allow ourselves a little wonder that minds like ours can ask questions this large and make progress that is this precise. So we carry on. Let's bring the abstract gears of eternal inflation down to where they turn the lights on down, to the conditions that make stars burn calmly for billions of years, that let carbon form, that leave room in the calendar for biology to try its long experiment. The grand claim that we inhabit one life-friendly patch among many only earns its keep if we can say what life-friendly really means, at least in broad strokes, and why those strokes are so narrow. This is where the quiet precision of physics does its best storytelling. Start with a deceptively simple constant, the vacuum energy, the cosmological constant. Push it even 100 or 1,000 times larger than we observe, and structure formation suffers. Gravity begins sculpting clumps out of the primordial mist, but the accelerated expansion tears them apart before they mature. Make it negative with a large magnitude, and the universe recollapses, briskly lights out, before stars have learned to write in photon. That narrow window, small and positive near the value we measure, sits right where galaxies can form, yet expansion still accelerates in deep time. A multiverse picture would say most patches miss some hit, and observers appear almost exclusively in the rare hits. The logic is spare and a little startling, like a haiku that happens to be true. Move to the ratio of forces. If the strong nuclear force were a few percent weaker, deuterium becomes fragile. The cosmic alchemy of the first few minutes fails to seed enough helium. Stars struggle to ignite the fusion chains that build heavier elements. If the strong force were a few percent stronger, almost all hydrogen would fuse in those same first minutes, leaving a cosmos short on the simplest fuel that stars sit for so long. Tip the electromagnetic force, and you perturb chemical bonds, the terraces on which organic molecules live. Adjust the proton to electron mass ratio or the fine structure constant by even modest amounts, and the stability of complex atoms begins to wobble. This is not numerology. It is the felt grain of the equations. Small shifts cascade through nuclear synthesis, stellar interiors, and the periodic table. Our particular carving through parameter space is not carved for us, but it is one of the few carvings that leave room for us. So in a landscape where different bubbles explore different values, you expect observers clustered in these narrow corridors. Stellar lifetimes are the most generous gift of all. There's a quiet miracle in the fact that middling stars like our Sun sip fuel slowly enough to grant billions of years to chemistry. If fusion rates were broadly faster, the era of starlight would be a sprint, not a marathon. If slower, perhaps stars would be too feeble to drive climate cycles and photosynthesis on rocky worlds. The stability of nuclear resonances matters too. The famous triple alpha process, 2 helium nuclei collide to make beryllium, which is unstable. But if a third helium arrives just in time and a particular resonance sits at just the right energy, carbon is born. Walks a delicate line. Shift the relevant energy levels by a few percent and you suppress carbon or oxygen production in stellar cores. It's fashionable to debate how finely tuned those resonances really are under broader changes to the constants, because many parameters co-vary in a full theory. But the thrust remains: you cannot fling the knobs just anywhere and expect the same music, the same delicacy threads through planetary habitability. The ratio of photon to baryon number in the early universe fixes, among other things, when the first atoms form and how the primordial fluctuations translate into the clumpiness of matter. That in turn influences the mass function of halos, the dark scaffolds on which galaxies assemble. Too clumpy and you get a universe of violent frequent mergers that destabilize planetary systems. Too smooth and you get meager, anemic structure where heavy elements are rare. Even neutrino masses, ghostly as they are, matter to the growth of structure. Too heavy and they smear out the small-scale seeds, shifting the tapestry on which galaxies embroider their spirals. The conditions for quiet, long-lived disks where rocky planets can persist and keep liquid water at the right distance from a stable star are not comedic coincidences. They are the downstream effects of numbers that sit in oddly narrow places. None of this proves a multiverse. It simply sharpens the question of explanation. In a single universe picture, we ask for a dynamical reason symmetry principle mechanism that pins the constants into the life-friendly corridors. In a multiverse picture, the explanation may factor a deep theory that permits a broad distribution of possibilities, plus a selection effect that filters for observers. Importantly, the two attitudes are not enemies. In the best case, a deeper theory would reveal why the distribution looks the way it does, which values are accessible, and which correlations are generic, such that selection becomes quantitative rather than a shrug. The right posture is not to canonize anthropic arguments, nor to ban them as heresy, but to use them judiciously where the structure of the theory makes parameters environmental. There is also a practical issue of reasoning that many of us find both subtle and oddly satisfying: how to think about typicality. When we say we should be typical among observers who can exist, we are smuggling in an assumption about sampling. Typicality is not a law, it is a prior. In data analysis, we handle such assumptions with care. We frame predictions as conditional statements and track how sensitive they are to the choice of measure, how we count, and to the choice of reference class, what counts as an observer like us. This Bayesian humility isn't philosophizing for its own sake. It guards against overconfident claims in a situation where infinities beckon and our sample size is 1. So when you hear, because we have to be read it as conditional on our existence, some otherwise surprising features of our world are no longer surprising, and keep one hand on the mathematics. Let's return for a moment to the earliest light, because it remains the cleanest test harness we possess. The Afterglows map is not just a pretty picture, it is an atlas of the primordial fluctuations. The spectrum's tilt tells us about the slope of the inflaton potential. The absence of strong non-Gaussianity tells us about interactions and how many fields were active. The tight limits on isocurvature mean the inflaton did most of the seeding alone, or that any companions were choreographed delicately. Add in upper limits on the tensor to scalar ratio, the loudness of primordial gravitational waves, and you already corner families of models. If tomorrow we discovered a small but unambiguous B-mode pattern consistent with inflationary gravitational waves, the inference would be immediate. The characteristic energy scale of inflation sits not far below the grand unification. Scale and our theoretical attention would focus on potentials consistent with that height. If instead the silence continues and the upper limits shrink, we will favour lower energy models, perhaps with fields that wander only short distances in their potentials. In either case, the arena narrows. The late universe answers back too. Measurements of how galaxies cluster and how they lens background light let us infer how the initial ripples grew under gravity. Those growth histories depend on the composition of the universe, on the coldness of dark matter, on the lightness of neutrinos, on the smoothness of dark energy, and by implication cross-check the early conditions. If there are persistent tensions, growth inferred from lensing that is lower than what the microwave background suggests, for instance, we investigate carefully. Are we seeing systematics in the data? If not, do we need to modify our account of gravity on cosmic scales or add degrees of freedom to the dark sector? Either path circles back to the early universe because any change to gravity or content alters the rules by which inflation seeds sprout. Cosmology is a web. Tug a thread in the present and the early universe quivers. A word about beginnings because the phrase eternal can tempt us to avoid them. Eternal inflation, as we've said, is eternal to the future. It keeps budding new regions, but the past boundary remains. Theorem suggests that inflating spacetimes are past incomplete. A beginning of some kind still lurks. Proposals abound tunneling from nothing in a precise quantum cosmological sense. No, boundary conditions in which the earliest times are Euclidean, with time behaving like a spatial direction. Initial states that pick out smoothness without classical fine-tuning. What is vital here is to keep the standards a proposal is physics only when it spells out a well-posed calculation, ideally one that touches data even indirectly. Until then, beginnings are a laboratory where quantum gravity will either vindicate our hunches or teach us something stranger. Strangeness takes a more playful form in thought experiments, like Boltzman brains, but even those serve as guardrails. A viable cosmology must not drown ordinary observers in seas of wildly atypical ones. That requirement constrains the asymptotic behaviour of the universe, the decay rates of metastable vacua, and the long-time thermodynamics of de Sitter, like spaces. It is remarkable that a whimsical idea about disembodied observers becomes, on inspection, a set of inequalities your model must satisfy. Now, you may reasonably ask what would change my mind, what observation would push us away from inflation entirely, and with it, the global gloss of eternal inflation, a clear, robust detection of large, strongly scale-dependent non-Gaussianity of a type incompatible with single-field slow-roll dynamics would be a start. Convincing evidence for a blue-tilted scalar spectrum that is more power on small scales than on large in conflict with all inflationary expectations would be another. A consistent alternative that reproduces flatness seeds and the microwave sky statistics while explaining the absence of relics without a period of accelerated expansion would also do it. Science thrives on such crisp alternatives. We haven't found them yet. Instead, each new survey tends to tighten inflation's jacket rather than tear it. What about nearer horizons, our own solar system biospheres on exoplanets, the chemistry that quietly assembles complexity? Here, cosmology steps back a little and lets astrophysics and biology lead. But the bridge remains the distribution of planetary systems, the metallicity of their host stars, the frequency of quiet stellar neighborhoods, the longevity of habitable conditions. All of that flows from the way structure formed, which in turn flows from the initial conditions. It is entirely plausible that the multiverse, if real, would predict correlations between constants and the prevalence of habitable worlds that we might in time test statistically. Imagine a future in which we can measure life's fingerprints across thousands of worlds. Even a hint of correlation between habitability and, say, the amplitude of primordial fluctuations encoded indirectly in galaxy environments would turn the philosophical into the empirical. We are not there today, but it is not a fantasy to imagine getting closer. Through all of this, there's a discipline worth voicing plainly. Ideas as broad as eternal inflation attract both hype and backlash. The remedy is neither to evangelize nor to dismiss, but to keep doing the hard, quiet work. Make the models precise, confront them with data, be explicit about assumptions, cultivate alternatives that are equally precise, and keep the rhetoric modest. Saying, "This could be how nature writes," is not the same as saying, "This is the only way nature could write." The universe has surprised us too many times for arrogance to be anything but an impediment. If there's a personal note to strike here, it's this: the scale of the questions is vast, but our method is small and local. We build instruments that listen for whisper-faint polarizations in ancient light. We point telescopes that count galaxies by the millions and weigh invisible matter by its lensing of background shapes. We collide particles to infer the couplings that shape the first fraction of a second. We argue, we check, we change our minds. It's wonderfully mundane for a subject so grand, and perhaps that's why it works. The cosmos, however large in possibility, must still pass through the needle's eye of careful measurement to enter our understanding. So where do we walk next? Step by step toward more sensitive microwave polarization experiments capable of hearing a tensor signal if it's there 100 times fainter than any thunderclap we've yet recorded. Toward wider, deeper galaxy surveys that map the late-time web with such fidelity that tiny deviations from our standard growth story will stand out if they exist. Towards sharper constraints on neutrino masses and hierarchies, because even these wraith-like particles tug on the cosmic tapestry. And toward theories of quantum space-time that turn the current measure problem into a solved exercise rather than a conference pastime. The list is long, but it is deliciously concrete. If eternal inflation describes reality, then our quiet, flat, long-lived bubble is one blossom in a garden that keeps seeding itself. If not, another story, equally subtle, equally surprising, waits over the horizon. Either way, the work ahead is the same test, refine, prune, repeat. And perhaps in the pauses between equations and observations, let the scale of it all settle. Not to overwhelm us, but to remind us that intelligence grew here on a small world, under a yellow star, and learned to ask questions so large that even the asking feels like a kind of participation. So let's carry that thread forward and pull on one more strand that connects the earliest moments to our present sky. How quantum fluctuations, those microscopic jitters, became the grand architecture of galaxies, and what that tells us about the deep quantum nature of space-time itself. Let's tug on that strand, how a universe that begins with microscopic jitters can grow a cathedral of galaxies, and what that quietly says about the quantum nature of space-time. The most astonishing claim of inflation, and the one that's paid its bills most handsomely, is that quantum fluctuations, those irreducible uncertainties that prevent a field from being exactly still, were stretched to astronomical scales and became the seeds of everything. This sounds like sleight of hand until you follow the steps. In an inflating space-time, every light ruler shrinks in usefulness, while the scale factor balloons. A wave mode that begins deep inside the horizon, oscillating like a tiny violin string, is redshifted until its wavelength becomes larger than the horizon itself. Once outside, it can't complete an oscillation. The dynamics freeze, and the mode's amplitude is imprinted as a nearly constant perturbation. Later, when the universe slows and the horizon grows, those frozen ripples re-enter, and gravity translates a little more density here than there into a cosmic scaffolding. There's a precise language for this, written not in poetry but in curvature perturbations, quantities that tell you how the local expansion deviates from place to place. The equation governing those perturbations is elegant, a single dynamical variable that packages up metric wiggles and field fluctuations, obeying a wave equation in a time-dependent background. Choose a well-motivated initial state, the vacuum appropriate to very short wavelengths, in a gently curved patch, and the quantum mechanics does the rest. The solutions squeeze as modes exit the horizon, one combination of the field, and its momentum is increasingly determined, the other increasingly uncertain. That squeezing is why by the time a mode has been outside for a while, its value behaves like a classical random variable, drawn from a distribution even though its origin is quantum. Decoherence interaction with a bath of many other modes seals the deal, burying quantum phases and leaving behind an effectively classical field of initial conditions. The result is a Gaussian random field with a nearly scale-invariant power spectrum, statistically simple, rich in consequences. Those consequences are everywhere in the oldest light. The hot and cold mottling of the cosmic microwave background is a portrait of the primordial curvature perturbations projected through the physics of the early plasma. Sound waves' pressure ripples raced through that plasma before atoms formed. Where compression was caught mid-beat when photons decoupled, we see a hot spot. Where rarefaction was frozen, a cold spot. The pattern is not arbitrary. It carries a series of acoustic peaks at angular scales set by the sound horizon, the distance those ripples could travel modulated by the matter and radiation content of the universe. That's why measuring the detailed multipole spectrum is so powerful. It lets us read off the initial conditions, the geometry and the contents all at once. It is a triumph of the idea that quantum mechanical whispers stretched across the sky can dictate statistics we can measure, to a precision of parts per million. Even the slight departure from perfect scale invariance, the tiny tilt in the spectrum, has meaning. It tells us about the slope and curvature of the potential that drove inflation. If the slope is gentle and the field rolls slowly, the tilt is small and negative a bit less power on small scales than on large. The numbers we infer are consistent with that slow roll picture, which is why so many models that predict violent features or dramatic non-Gaussian shapes have fallen away. Non-Gaussianity, for its part, is a stall test for Baroque dynamics. Interactions among modes' multiple active fields or sharp features in the potential can imprint distinctive 3-point and 4-point correlations, triangles and quadrilaterals of temperature fluctuations with preferred amplitudes and shapes. The sky has been notably reluctant to reveal them in strength. That reticence has been instructive. It's narrowed the viable inflationary corridors to those in which the field's journey was smooth and solitary, or in which companions were choreographed with exquisite subtlety. But the story doesn't end when the photons decouple, when those curvature perturbations re-enter the horizon during the matter-dominated epoch gravity takes over. Regions slightly denser than average pull in more matter, which makes them denser still. The mathematics of linear growth is clean density contrast, grows proportional to the scale factor in a matter-dominated universe until non-linearities awaken and halos form. Embedded in this evolution are further diagnostics of the initial conditions. The acoustic ripples in the early plasma left a fossil in the late-time galaxy distribution, a preferred separation scale known as baryon acoustic oscillations. Measure the clustering of millions of galaxies and you see a faint bump at that separation. It's a standard ruler you can carry across cosmic time to map out the expansion history and cross-check the initial spectrum. Weak gravitational lensing, the subtle shearing of galaxy shapes by intervening mass, traces the same growth from another angle. These late-time tools ask, did the seeds that inflation claims to have planted sprout in the way general relativity predicts in a universe filled with cold dark matter and a smooth dark energy, so far within uncertainties that are tightening year by year? The answer is yes. Now, because we are aiming at truth rather than comfort, we should talk about the quantum to classical step with the same sobriety we give everything else. It's tempting to say the modes become classical when they freeze, but that is a metaphor with homework underneath. The homework is decoherence show that the squeezed quantum state of long wavelength perturbations, when coupled to a sea of short wavelength modes and other fields, loses its quantum interference in the variables that matter for observations. Calculations show exactly this. The squeezing makes the perturbations extraordinarily sensitive to environmental nudges. The phase information that would betray quantum coherence is dispersed into unobserved degrees of freedom. What remains is operationally classical random phases and amplitudes drawn from a distribution transported forward by deterministic equations. It's a beautiful answer to the question, how did the universe pick one concrete pattern out of a quantum ensemble? It didn't. It picked many in different Hubble patches, and we observe one realization. So the randomness in our sky is not ignorance of a classical mechanism. It's the fingerprint of quantum origin. The path from seeds to stars also runs through the dark sector. If dark matter is cold, moving slowly in the early universe, then it happily clumps on small scales and provides deep potential wells into which baryons fall cool and form galaxies. If it were warm or hot, free streaming would erase small-scale structure, delaying the formation of the first galaxies and changing the pattern of satellites. That sensitivity to the dark matter's properties means the early universe script is not a monologue, it's an ensemble piece. Neutrinos, light but not massless, also leave their signature by damping power on small scales. The mass sum of neutrinos subtly slows growth. Measure the growth with enough precision and you weigh the neutrinos cosmologically. In that sense, the seeds inflation plants become diagnostic tools, not just for inflation itself, but for particle physics we cannot reach with colliders. Reheating sits at the hinge. Inflation ends, the inflatant's energy decays into the standard model and perhaps other fields. The universe becomes a hot plasma again. The exact channels and couplings matter because they influence the temperature achieved and the species produced. A hotter reheating can revive symmetries and interactions that a cooler reheating would not, leaving different relics in the particle zoo or different imprints in gravitational waves. There is a dream, ambitious but not absurd, that fine-grained measurements of the microwave background's polarization and spectral distortions, combined with gravitational wave surveys across a span of frequencies, could reconstruct aspects of the reheating history. If that dream comes true, we will have turned the end of inflation from a phrase into a measured epoch. And where in all this does the global gloss of eternal inflation re-enter? It re-enters as an inference about what the same mathematics does outside our horizon. If the slow roll conditions were met here, they were plausibly met elsewhere. If quantum fluctuations helped the field linger high on its potential here, they plausibly did there. Eternal inflation says this lingering coupled to exponential expansion makes the production of new regions inexhaustible. The profound thing is that we do not need to see those regions to test the premise. We need only be relentless about testing the inflationary scaffolding. We can reach the near scale invariance, the small non-Gaussianity, the single clock behavior implied by minimal isocurvature, the presence or absence of a primordial tensor background, the consistency between early and late growth. If those pillars stand, the global picture remains viable. If one fails decisively, the picture must change. There are to be honest hints of tension at the percent level in some late-time growth measurements. Some lensing surveys whisper that structures grew a touch more slowly than the simplest model extrapolated from the microwave background would suggest. These whispers are not verdicts, they are invitations. We treat them with suspicion of systematics, with cross-checks across instruments and methods, and only then with theoretical imagination. Perhaps dark energy evolves slightly, perhaps neutrinos are a shade heavier than expected, perhaps modified gravity makes a cameo on large scales. Any of those adjustments, if confirmed, would ripple backward to the initial conditions, tweaking the inferences we draw about the inflationary potential. The web is tight, a tug here is felt there. The discipline is to follow the tug with equations rather than declarations. Let me end this turn by turning the telescope around. The question, how did quantum jitters become galaxies, is in one sense the most practical expression of a deeper question, is space-time itself. A quantum object, inflation answered with a resounding, it had better be, or none of this makes sense. The oldest empirical evidence we possess for the quantum nature of fields in the universe is etched across the sky as a billion-year-old interference pattern frozen and then thawed by the expansion. That is a thought worth pausing over. We did not merely fit a model to some data, we read quantum mechanics in the microwave haze. So when we push onward to quantum gravity, to the measure problem, to beginnings, to horizons and information, we are not importing quantum fancy into an unwilling cosmos. We are following the logic of what the sky has already told us patiently, with the same habit of mind that took us from small ripples to a map of everything. Let's follow the logic where it naturally leads to horizons, heat and information, because the moment you admit that quantum fluctuations wrote the first draft of our cosmos, you're compelled to ask what happens to information at the edges of what any one observer can see. Inflation, even without its eternal extension, hands each of us a cosmic horizon, a boundary beyond which events can never influence us because space between is expanding too quickly. That is not merely cartographic, it's thermodynamic. A horizon behaves like a physical object with temperature and entropy. This is one of the strangest, most beautiful discoveries of 20th century physics. Horizons aren't just lines on a diagram, they have heat. We first learned this in the context of black hole. A black hole classically is a one-way membrane. What goes in cannot come out. But when quantum mechanics joins the party fluctuations near the horizon, give rise to a trickle of radiation, Hawking radiation with a temperature inversely proportional to the black hole's mass. Equally astonishing, the entropy of the black hole, the measure of how many microscopic states correspond to the macroscopic thing, scales with the area of the horizon, not the volume in natural units. Entropy likes to count bits. Area is counting boundary tiles. The lesson is deep gravity, quantum mechanics and thermodynamics are entangled in ways that remodel our intuition about inside and outside. Inflationary space on the largest scales shares this character. A universe dominated by vacuum energy, Ardha-Sitta-like state, has a cosmological horizon with a temperature and an entropy proportional to its area. That means there is an intrinsic heat of expansion, a bath so faint that no living creature will notice it, but so real that the equations insist upon it. For a local observer, the horizon radiates like a thermal surface with a temperature set by the Hubble rate. You could, in principle, hang a very patient thermometer at the edge of forever and get a reading. That reading is tiny today, far, far below the microwave background, but in the inflationary past it was huge. This is not a curiosity, it is a clue. If horizons have temperature and entropy, then the degrees of freedom of space-time are not like the molecules of air in this room. They are organized in a way that makes areas count bits. That's the seed of holography, the idea that the information content of a region is coded on its boundary. Now, holography is most sharply formulated in spaces with negative curvature at infinity, where a dual description without gravity, the celebrated correspondence between a gravitational theory in a bulk and a quantum field theory on its boundary, has been demonstrated with mathematical precision. Our universe on large scales is not of that type. But the hints from black holes and de Sitter horizons whisper that a holographic bookkeeping might still be the right language for cosmology. If that's true, it changes how we think about eternal inflation at a fundamental level. Instead of imagining a God's eye view of an infinite froth of bubbles expanding without end, we ask a more modest question. What is the complete description of everything? An observer within one horizon can even in principle measure. The causal patch viewpoint says focus on what fits in the patch, count information at its boundary, avoid global infinities that may be artifacts of pretending we can stand outside the universe and tally. This shift of perspective does not settle the measure problem, but it reframes it. If probabilities are to be defined for observations made by observers in a horizon patch, then the relevant count should emerge from the quantum mechanics of that patch and its boundary data. The promise is that a proper, fully quantum description of space-time will not ask you to compare infinities. It will hand you finite answers because it never leaves the domain where physics is operationally defined. We are not there yet. We have toy models, we have conjectures, we have suggestive calculations in simplified settings. But the direction of travel is clear. Gravity wants to be counted at the boundary. Why am I pressing on this? Because it links the early inflationary story to the later puzzle of dark energy and to the deepest riddle of all, whether information is ever lost. Black hole evaporation forced us to confront that question. A pure quantum state falling into a black hole appears to be destroyed if the whole radiates away thermally, leaving only featureless heat. But quantum mechanics abhors loss of information. It demands unitary evolution. Across decades, the community wrestled with this apparent conflict, the information paradox, and learned to read the boundary better. The modern consensus is cautious, but hopeful information is not destroyed. It is encoded in exceedingly subtle correlations among the Hawking quanta correlations that a semi-classical calculation misses. In other words, the paradox points to the need for a quantum description of space-time in which horizons do not obliterate information, but rearrange it in a way that looks thermal to coarse observers. Carry that lesson back to cosmology. Our horizon, like a black hole's, has entropy and temperature. If our patch is a finite quantum system, then anything that falls beyond our horizon is not lost in a fundamental sense. It's entangled with the degrees of freedom that live on the boundary of our observable world. Eternal inflation in a holographic light becomes less a map of endless territory and more a statement about the entanglement structure of many horizon patches. Bubbles that we cannot see may still be part of the same quantum state, stitched together not by causal contact but by shared origin in the deep theory. That's poetic language for a technical goal to write the Hilbert space, the space of quantum states for a cosmological region in a way that captures its finite information content and the rules by which it exchanges information with its horizon. Let's be concrete about what this could mean observationally. De Sitter temperature today is absurdly small, yet the presence of a horizon implies that ultra-long wavelength modes fluctuations larger than our horizon should influence local statistics in constrained ways. In practice, the effects are minute. The sky we see is dominated by sub-horizon physics at recombination and later. But there are clever consistency relations, equalities, that must hold among correlation functions if a single clock, the inflate and set the initial conditions, and if super-horizon modes play the limited role inflation predicts. Precision tests of these relations are ongoing. A violation would be electric. It would say the early universe had more than one active field, or that some long-mode physics beyond the simplest inflationary story bled into local observables. So even the invisible beyond horizon world has a subtle way of tugging on what we can measure, and we're learning to feel for that tug. Another frontier sits at the interface of quantum information theory and cosmology. Over the past decade, ideas like entanglement, entropy, quantum error correction, and computational complexity have leapt from abstract mathematics into the language of space-time. In black hole physics, we've learned to compute the fine-grained entropy of Hawking radiation using quantum extremal surfaces, geometric objects that seem to know about entanglement in a dual description. This machinery has begun to be applied to cosmological horizons as well, with early results that hint at how information might be parceled between an observer's patch and the rest of the inflating space. The technical details are young and delicate, but the philosophical upshot is sturdy. If space-time is built out of entanglement, then the growth and branching of inflating regions should be described in that same quantum informational grammar. Eternal inflation becomes in this view a story about how quantum states fragment and diversify under the twin pressures of expansion and decoherence. Now, before we drift too far into the abstract, let's anchor again in the sky. There is a humble, testable reason to care about horizons that radiate they can, in principle, generate real particles. During inflation, the rapid expansion and the associated horizon temperature excite fields producing fluctuations not only in the inflaton, but in any sufficiently light field present. If some of those fields survive into later epochs, say as relic particles or as isocurvature perturbations, they leave footprints. This gives us a way to rule in or out entire families of high-energy physics. If we detected an isocurvature component, ripples in the relative abundance of, for example, dark matter versus photons, it would signal additional light fields active during inflation. Thus far, the sky prefers a single clock narrative with isocurvature tightly limited, which simplifies the story and in a way trims the more baroque branches of eternal inflation that rely on many active fields, painting wildly different interiors. There's also the question of vacuum stability in a universe that may spend long ages in de Sitter-like states. If our low-energy vacuum is metastable, then somewhere in the world picture there exist bubbles of a lower vacuum that expand at nearly the speed of light, converting space as they go, like the bubbles I described earlier, but now as an existential hazard. In the strict mathematics, a single such bubble entering our horizon would end our local physics abruptly. The probability is thought to be tiny on timescales vastly exceeding the current age of the universe, but eternal inflation is a kaleidoscope in which all such processes happen somewhere. This makes the precise decay rates and couplings non-academic. They're part of the consistency conditions for any global story. The universe must be arranged such that ordinary observers arise in large numbers long before vacuum decay makes their existence improbable. That demand folds back into constraints on high energy parameters in the inflationary scale. The web tightens again. You might wonder whether all of this structure, horizon entropy, holography, information bookkeeping has any bearing on the values of the constants themselves. Here's a suggestive thought. If a horizon has a maximal entropy proportional to its area, then a universe with a larger cosmological constant has a smaller horizon and thus a smaller entropy bound. In very loose terms, such a universe has less room for complexity in the sense of distinct, long-lived configuration. That does not explain our vacuum energy, but it frames a selection effect in a new light patches with very large vacuum energy are not just bad for structure formation, they are bad for information storage, period. Our patch with its tiny vacuum energy and vast horizon is an information-rich environment. Life and intelligence are, in that sense, entropy artists. They record, process, and transmit patterns. A cosmos that grants a generous canvas is the only place those artists can work. The multiverse then becomes not only an ensemble of different low-energy laws, but an ensemble of canvases of different sizes. Let's pull the thread of beginnings once more, but now with the language of horizons in hand. If inflating space is past incomplete, as the theorem suggests, then any full account must specify an initial quantum state. In laboratory physics, initial states are often chosen for convenience. In cosmology, the choice is physical. The no-boundary proposal, for example, imagines that near the origin, the distinction between time and space blurs. The universe is described by a compact geometry without a boundary, and the probability of different classical histories is weighted by the exponential of a Euclidean action. Another proposal invokes tunneling the universe nucleates from nothing, not a pre-existing space-time, but the absence of classical geometry, into a small, inflating patch. Both ideas attempt to compute measures probabilities for inflation to begin, for the number of e-folds, for the curvature, and even for the spectrum of fluctuations. Neither is universally accepted. Both have technical hurdles, but they are admirable because they try to turn metaphysics into mathematics. If one can be made precise and productive, it might also illuminate how to count in an eternally inflating setting without cheating with infinities. Meanwhile, the experiments carry on wonderfully oblivious to our metaphysical preferences. The next generation of microwave polarization observatories will either hear the whisper of primordial gravitational waves or set upper limits so exacting that entire classes of inflationary potentials will go quiet forever. Galaxy surveys will chart cosmic acceleration and growth with percent-level precision, telling us whether dark energy is a featureless cosmological constant or something with texture. Laboratory measurements will fix the neutrino mass hierarchy, cleaning up a nuisance parameter in cosmological inference. And radio arrays, listening for the redshifted hydrogen line, will attempt to map the cosmic dawn when the first stars switched on, giving us a new arena in which to test how seeds became structure. Each new constraint echoes back to the early universe, and each echo is a chance for inflation's scaffolding to wobble or to stand a little straighter. If you've been waiting for a moment of philosophy, here it is, but let's keep it honest. Eternal inflation horizons with heat holographic whispers. None of this says that our existence was intended. It says that the laws are such that many outcomes are realized, that selection effects matter when parameters vary, and that information is never a spectator in gravitational physics. It sits at the very table where geometry is decided. The meaning we make of that is ours to choose. For me, it fosters a kind of practical awe. Our bubble is quiet and old, its horizon is vast, its laws are gentle enough to let atoms dance for billions of years. In that environment, minds arose that can read the faintest imprints in ancient light and infer that quantum mechanics once wrote on the sky. So we keep reading with the understanding that the next line might revise the chapter, and the chapter might revise the book. And perhaps this is the most enduring lesson the cosmos offers. The universe appears to be outrageously large in possibility, yet parsimonious in the rules it uses to write. Out of those rules come horizons with heat black holes that count their bits on their skins, inflating patches that plant quantum seeds, and late-time webs of galaxies that echo acoustic notes from the first 100,000 years. If a deeper holographic script underlies this all, then learning to read it will not only settle arguments about measures and beginnings, it will deepen the quiet confidence with which we say, "Here is how we know." The future of this story is empirical and mathematical, not rhetorical. And the path forward is simple in spirit, even when it is complex in practice measure. More calculate, better welcome surprise. The truth, if it is to be earned, will be earned that way. Let's turn from what horizons mean to what we can actually do with them, how we turn a dizzying global picture into concrete local predictions that survive contact with the sky. Because if the story is to be more than an elegant rumour, it has to pay rent with numbers, with patterns in old light, with the growth of structure, with clocks and rulers we can build. And it has to explain why some things are impossible to learn cosmic secrets fenced off by horizons, not as a failure of curiosity, but as a feature of the physics. Begin with a humbling fact. Even a perfect theory of the early universe cannot predict the exact temperature of each pixel in the cosmic microwave background, or the exact position of each galaxy in the night sky. The primordial fluctuations are fundamentally random draws from a distribution. What the theory predicts are the statistics of those draws, the mean, the variance, the correlation functions. This statistical nature is not a concession, it's the signature of the quantum origin of the seeds. But it introduces a delicate limit called cosmic variance. If there is only one sky to observe one set of draws, then even with flawless instruments, we cannot know the exact ensemble averages better than the scatter allowed by having just a single realization. On the largest angular scales, where there are very few independent modes across the sky, cosmic variance is a stern ceiling. This is why, for example, the error bars on the very lowest multipoles of the microwave spectrum are large, not because our telescopes are shy, but because the universe is finite for us. Cosmic variance is the gentle voice of the horizon saying, this is as far as knowledge can go from here. That limit could sound like a discouragement, but it's also a precise guide. It tells us where additional effort pays diminishing returns, and where fresh techniques can leap the wall. One leap is to measure new fields, not just temperature, but polarization, not just the sky, but the three-dimensional distribution of galaxies and the weak lensing shear field. Each independent field supplies new modes, new draws, and thus new opportunities to tighten statistical screws. Another leap is to use standard rulers and standard candles, baryon acoustic oscillations and supernovae to triangulate cosmic expansion with geometric exactness, cross-checking the inferences drawn from primordial statistics. In that way, we weave a net of independent measurements that collectively squeeze the allowed space for early universe models until only the nimble survive. Now place eternal inflation under that net. The accessible leverage points lie along four beams. First beam, the single clock nature of the initial conditions. In the simplest inflation, one clock the inflaton sets the timing for all regions. That uniform clocking enforces relationships among correlation functions. A long wavelength mode that looks like a uniform rescaling of coordinates should not locally change small-scale statistics beyond trivial effect. These are the consistency relations. They are weak to test, but merciless when broken. A clean violation would mean either additional light fields during inflation or interactions sharp enough to break the single clock picture. Many eternal inflation scenarios still respect the single clock locally, others do not. So precision tests of consistency relations in the microwave background and in the large-scale structure are an elegant sieve. So far the sky whispers single clock within current precision. Second being the loudness and shape of primordial gravitational waves. If future polarization experiments detect a tensor signal and fix the tensor to scalar ratio, we'll measure the characteristic energy scale of inflation. High energy often correlates, though not rigidly, with dynamics that make eternal behavior more likely, because quantum fluctuations can more easily hold the field aloft on the high parts of its potential. A non-detection down to very small levels favors low energy inflation that may be less prone to eternal behavior depending on the potential shape, either way we prune. The point isn't that gravitational waves prove or disprove eternal inflation, but that they steer us toward the parts of theory space where eternal behavior is plausible or rare. The pruning is the progress. Third beam isocurvature and extra fields. If any relic signature of additional light fields from inflation survive distinct ripples in the relative abundances of species or specific non-Gaussian shapes, then the plain vanilla single field story is incomplete. That would embolden models in which the landscape is richly populated during inflation, strengthening the hand of those versions of eternal inflation where different fields choose different low energy phases in different bubbles. So far, sensible upper limits have kept that exuberance in check, but it's a live test and one that will sharpen with new data. Fourth beam curvature and scars. A bubble born by quantum tunneling generically begins with negative spatial curvature inside. Rapid expansion can wash that curvature down to undetectable levels, but not if the number of E-folds after nucleation was too small. The current bounds tell us our curvature, if any, is tiny. Push those bounds tighter and you corner the needed expansion in our patch, which in turn constrains the landscape of viable bubble histories. Searches for collision scars, circles in the sky. Faint anisotropic modulations are cruder, but improving statistical hygiene keeps the door open. A non-detection tightens the leash on scenarios that predict abundant, strongly imprinted collisions in our past light cone. Threaded through all of this is a philosophical pitfall we should name and walk around the temptation to use the multiverse as a universal solvent for puzzling numbers. The proton to electron mass ratio looks curious. The fine structure constant sits just so. The vacuum energy is absurdly small. It's easy to say they vary across bubbles. We live where they work. Sometimes that may be right, but the discipline is to earn every such appeal, show that the parameter is truly environmental in the candidate high energy theory. Compute the distribution across vacua. Specify the selection function, what it means to be an observer. And then confront the resulting predictive correlations with data. Hand-waving here is not a minor sin, it's an invitation to stop looking for deeper dynamics prematurely. The ethos is symmetry first, selection last. When symmetry fails to fix, selection may step in, not the other way round. With that ethos, let's revisit the youngness and runaways that haunt eternal inflation's probability bookkeeping. If new bubbles are constantly formed in an inflating background, and if the background expands exponentially, you might worry that the multiverse is dominated by extremely young regions, freshly minted bubbles, outnumbering old ones at any finite cosmic time cutoff. That's the youngness paradox. As with all measure problems, the remedy isn't to shrug, it's to find a counting scheme tied to an observer's patch or to a physically motivated slicing of space-time that washes out the paradox. Causal patch measures scale factor cutoffs. Light cone time measures, all of these are earnest attempts to extract finite answers from infinite tails while respecting the causal structure. They are not all equivalent. Some lead to absurd predictions. Some survive contact with basic sanity checks. Here again, the holographic hunch helps define probabilities in terms of boundary data for a patch, and the ghastly infinities lose their teeth. The field is working toward a consensus, but it is not there yet. Saying we don't know is not a weakness. It's an accurate map of where the fog still lies. There's a second subtle trap opposite to the first despair about predictivity. You may hear, if many low energy laws are realized somewhere, then nothing is predicted. That's too strong. Even an ensemble can have sharp statements. Consider the vacuum energy again. If the distribution of possible vacuum energies is roughly flat across a range that dwarfs the narrow, anthropically allowed window, then observers will overwhelmingly measure values near the upper edge of that window, the largest values compatible with galaxy formation. That is a concrete, falsifiable statement. If we had found a vacuum energy 1,000 times smaller than the upper bound for galaxy formation, the simple anthropic explanation would look strained. In fact, the measured value is within a couple of orders of magnitude of that edge, suggestive, not decisive. Similar ensemble predictions exist for the amplitude of primordial fluctuations and for the timing of matter. Radiation equality, though they are entangled with assumptions about the distribution. The moral is modest, but real ensembles can predict typicalities, and those typicalities can be checked. Let's come down from the high balcony for a minute and walk among instruments. What will actually shift our confidence in the scaffolding over the next decade? CMB polarization at the nanokelvin frontier. Experiments on dry plateaus and at the South Pole will rate the sky for the faint swirls of B modes. A detection at a tensor to scalar ratio above roughly a few parts in 1,000 would be epochal. Null results will still shear away loud corners of theory space. Stage 4 galaxy surveys and weak lensing maps. They'll chart hundreds of millions of galaxies, measure growth to the percent level, and in combination with lensing of the microwave background pin down the sum of neutrino masses cosmologically. If growth is consistently slow relative to the simplest model, we'll have to ask whether dark energy has texture or gravity needs an infrared amendment. Either answer propagates back to early times. The 21 centimeter cosmology of cosmic dawn. Radio arrays listening for hydrogen's whisper will map the first luminous structures. The timing and patchiness of reionization carry information about small-scale power and thus about the initial spectrum and about ingredients like warm dark matter that blur the tiniest seed. Direct gravitational wave backgrounds beyond the microwave band. Space-based interferometers and pulsar timing arrays probe frequencies that inflation might have energized through features or through phase transitions during reheating. A confirmed background with the right spectral shape would be a treasure map back to a specific epoch. All of these are local, humble in their way. None peers into a neighbouring bubble, yet each, by tightening the bolts on the inflationary framework, either leaves room for eternal behaviour to be a plausible corollary, or forces us to redraw the early universe chapter more radically. That's the right sequencing. We do not aim to prove a multiverse. We aim to be ruthlessly precise about the piece of cosmology we can test and let the global corollaries stand or fall with their scaffolding. A word on endings, because the question why are we here is cousin to how long will anything like us be here? If our vacuum energy is truly constant, the far future is a quiet, de sitter expansion. Galaxies beyond our local group will drift over our horizon. Background radiation will cool and redshift into darkness. Stars will age. Black holes will evaporate over fantastically long times. It's a melancholy picture in which information is never destroyed but becomes ever harder to access, spread thinly across horizons and Hawking quanta. If, on the other hand, dark energy evolves, decaying away, or changing sign, new chapters open, slow return to matter dominance, or a catastrophic crunch. Eternal inflation complicates even this because, in the global view, many fates occur somewhere. But for us in our patch, the forecast is written by parameters we can measure. That is strangely comforting. The cosmos may be a grand branching tree, but the weather here is set by numbers we can read. And there is an ethical thread often left unspoken in physics talks, but present in the way these ideas land. A multiverse can be taken wrongly as an invitation to fatalism. If everything happens somewhere, nothing matters. The opposite is true. Meaning is local. It's made by finite beings in finite patches under finite horizon. The discovery that our patch is one among many, if it holds, doesn't dilute the significance of knowledge, it intensifies it. It says that within a bounded world, minds emerged that learned to read initial conditions off the sky, to hear the deep bass note of gravity in the shapes of galaxies, to weigh ghosts called neutrinos by their damping of structure, to imagine horizons as hot and information as geometric. That's a testament not to destiny, but to patient method and shared curiosity. So the practical upshot is not to wait for neighbouring universes to send a postcard, but to keep refining the craft that has taken us this far. Let me leave one more breadcrumb for where we might go next, the interface of time and information. If horizons store information on their areas, if the arrow of time is sculpted by inflation smoothing and gravity's clumping, And if decoherence turns quantum potential into classical fact as modes slip beyond horizons, then perhaps the right language for cosmology is neither purely geometric nor purely field theoretic, but informational. Perhaps initial condition is really a code, and history is decoding under constraints. That's not mysticism. It's the drift of serious work at the frontier where quantum information theory has already reshaped black hole physics. In the next turn, we can trace that drift more concretely, how entanglement, wedges, quantum error correction, and complexity might give us new handles on the early universe, and whether that language can finally tame the measure problem rather than merely rephrasing it. So let's carry that curiosity forward carefully and see whether an informational grammar can sharpen the oldest cosmic questions we have. Let's try to speak the universe's language in a dialect that's become surprisingly powerful information. Not information in the everyday sense of gossip or headlines, but information as physics uses it: entropy and entanglement, error correction and complexity. The bookkeeping that tells you how many distinct microscopic stories can hide behind the same macroscopic facts. This grammar has already transformed our understanding of black holes. Now it's beginning to seep into cosmology. If horizons have heat and count bits by area, if quantum fluctuations write the seeds of galaxies, then perhaps the early universe is best read not only as a geometry evolving in time, but as a computation unfolding within a code. Start with the quiet revolution that black holes forced upon us. We used to imagine a black hole as a simple grave, a place where information went in and never returned. Then the paradox sharpened our thinking. Hawking radiation looks thermal featureless, but a fundamental quantum theory cannot throw information away. The modern picture, still being refined, says that if you compute the fine-grained entropy of the radiation properly, allowing the geometry itself to contribute through quantum extremal surfaces, you recover a page curve entropy of radiation rises at first and then falls as correlations leak out in subtle non-local ways. The moral is precise: the boundary of a region knows about the information in the bulk, because space-time is in a sense stitched together by entanglement. That stitching looks suspiciously like quantum error correction, the same principle that keeps qubits safe in a noisy quantum computer. Translate that mood to cosmology. Our observable universe is a finite region framed by a horizon. If black hole horizons count bits and enforce careful entropy, bookkeeping cosmological horizons should too. The challenge is technical. Our horizon is not a rigid boundary inside a static box. It's an ever-changing edge in an expanding space-time. Still, the hints align. De Sitter space, the idealized cousin of our accelerating cosmos, has a horizon with a temperature proportional to the expansion rate and an entropy equal to its area in Planck units. If that entropy is a bound on the information you can stuff into a horizon patch, then a cosmological region is at heart a finite quantum system. We're not talking about simulation in the science fiction sense. We're saying the content of the patch can be encoded on its boundary in a way that preserves what local observers can measure. The code is not arbitrary. It reflects deep symmetries and the algebra of observables within the patch. That perspective encourages a shift in how we address eternal inflation's thorny infinities. Rather than pretending to stand outside the entire multiverse and count endless bubbles, an exercise that turns probability into a contest of incomparable infinities, we can ask a better question: what is the full, consistent quantum description of the degrees of freedom within a single causal patch? And how do we define probabilities for observations made by observers inside it? In that framing measure, problems become questions about state preparation, allowed operations, and the code that knits geometry and fields together. It's early days, but even this reframing trims the conceptual fog. It says, keep your eye on what can in principle be measured. Tether your counting to boundary data. Avoid quantities that ask a God's eye sum over unreachable regions. Entanglement makes another concrete appearance in inflation's most beautiful output, the nearly scale-invariant Gaussian pattern of primordial fluctuations. We talk about those modes as if they were random classical variables, and in practice that's right, but their origin is quantum entanglement. Inflation squeezes each mode one combination of the field, and its momentum becomes sharply defined as the wavelength stretches beyond the horizon, while its conjugate becomes wildly uncertain. The environment, the swarm of other modes and fields, decoheres the phases, so what remains is a classical-looking random field. But the randomness is not ignorance of a hidden classical mechanism. It's the living memory of quantum origin. That tells us something subtle. When we calculate correlation functions in the microwave background, we are already doing quantum information theory in the sky, whether we say so or not. we're reading entanglement patterns that inflation wrote. If entanglement is the glue error correction looks like the architecture. In holographic dualities, space-time regions are reconstructed from boundary data in a way that resembles a redundant code, lose a piece of the boundary, and you can still rebuild the interior, lose too much, and the bolt point slips out of reach. In black hole physics, this idea has bite. You can literally compute how much of the boundary you need to reconstruct a given bolt region. Cosmology is trickier, but the moral may carry the information accessible to an observer in a horizon patch is redundantly encoded in the degrees of freedom that live near the boundary of that patch. Disturbances noise get washed away by expansion and decoherence. The code protects the classical long wavelength facts that survive into the late universe, like the near-scale invariant spectrum. So when we talk about initial conditions, we might be better off talking about code words, specific robust patterns of entanglement that expand into the sky we see. Then there is complexity, an idea that sounds like philosophy until you try to compute it. In the black hole lab, complexity, roughly the length of the shortest quantum circuit needed to build a state from a simple reference, appears to grow long after ordinary thermodynamic quantities have saturated. Some conjectures link this growth to geometric features like the volume behind a horizon or the action of a region of space-time. If any echo of that persists in cosmology, it could give us a new handle on the arrow of time. Inflation sets up a low gravitational entropy state by smoothing the universe. From there, gravitational clumping and cosmic expansion drive entropy up, and perhaps complexity up too. The late-time universe might then be seen as a system still computing, still exploring larger and larger circuits, even as its coarse thermodynamic descriptors approach calm. That picture dovetails with experience. Galaxies assemble stars, forge elements, chemistry explores vast phase spaces, and life information processing par excellence arises. It's speculation, but it's a grounded one. Tie the abstract word complexity to geometric or observational proxies, and it becomes a testable language, not a metaphor. Let's make the informational grammar do work on a concrete cosmological riddle, the single clock consistency relations. In simple single field inflation, a very long wavelength mode acts like a smooth rescaling of coordinates for shorter modes. That implies exact relations among correlation functions constraints you can derive from symmetry alone. In information terms, the long mode is a background code word. Local observers cannot detect it except through trivial rescalings of their rulers and clocks. Violate the relation, and you've announced that more than one clock was active, extra light fields added independent phases to the code. Observationally, the sky largely respects the relations. Any violation is small within present errors. That's already an informational statement. Our initial conditions look like they were written by one dominant process, not a cacophony. And if a future survey finds a clean shape-specific violation, we'll know what kind of extra writer joined the pen. The form of the violation tells you whether it's multiple fields, sharp features, or something even stranger. Now take the same lens to the impossibility baked into horizons. Cosmic variance, the fact that on the largest scales we only have a handful of independent modes to measure, often sounds like a practical nuisance. It's more than that. It's the signature of finiteness, a reminder that a horizon patch contains only so many independent degrees of freedom. You can fight cosmic variance by measuring new independent fields, polarization, lensing, three-dimensional clustering, but you cannot abolish it. It's nature's way of saying the code's alphabet has a finite size in this patch. The upper limit on precision at low multipoles is not an experimental failure. It is a boundary law made manifest in our error bars. There's also a striking, almost playful implication when you combine these ideas with eternal inflation's broad brush. If our patch is a finite quantum system with a horizon area entropy, and if the global story involves countless such patches branching and decohering, then the multiverse is not an ocean of classical universes, so much as a vast, entangled state continually fragmenting under expansion. Different bubbles are not independent books on a shelf. They're chapters in a single quantum novel. They're texts orthogonal enough that no reader inside one chapter can reconstruct the others, yet all written in the same alphabet. In that sense, the question, do other bubbles exist, becomes a question about the structure of the global wave function rather than about distant places in space. And the right answer becomes modest. If the inflationary mechanism that wrote our patch operates generally, then the global quantum state likely contains many decohered branches with different low-energy code words. We cannot read them, We can infer their plausibility by stress, testing the mechanism that wrote ours. All of that remains abstract until we let instruments put pressure on it. Happily they will. Precision polarization maps of the microwave sky will keep hunting the faint swirling B modes that inflation's gravity waves would imprint. A detection measures the height of the inflationary potential. A tighter non-detection keeps whittling the family of potentials down. Either way, the number of viable code words shrinks. Three-dimensional galaxy surveys and weak lensing maps will test the single clock story by checking whether long-mode rescalings behave exactly as predicted across cosmic volumes. Deviations, if they appear robustly, would point at extra light fields or features telling us the code was bigger than minimal. 21 centimeter cosmology, the mapping of neutral hydrogen across early times, will watch the first luminous structures flicker on and spread their bubbles through the intergalactic medium. The timing and patchiness of that flickering depend sensitively on the small-scale power spectrum, and thus on the statistical DNA inflation left behind. And then there's the audacious frontier stochastic gravitational wave backgrounds across many frequencies. Inflation's own background might lie at frequencies too high or too low for some detectors, but reheating and any symmetry-breaking phase transitions could have generated distinct hum. Pulsar timing arrays have already glimpsed a low-frequency background of likely astrophysical origin. Space-based interferometers will open the millihertz band. Ground-based networks listen higher still. If a background with a primordial non-astrophysical spectrum is confirmed, we will have seized a second messenger from the early universe, independent of photons that can encode features of the code word written as inflation, ended so. So the informational script becomes multi-channel light and gravity together, spelling out the same story or deliciously exposing contradictions. There's a temptation to round this into a credo space-time is entanglement. Cosmology is code, but physics does not run on slogans, it runs on derivations that survive contact with data. The value in this informational grammar is that it points to derivations we can try to make sharp. Define a finite operational Hilbert space for a horizon patch. Derive the consistency relations as identities in that algebra. Compute fine-grained entropies for cosmological radiation fields using quantum extremal surfaces adapted to expanding backgrounds. Identify observational proxies for complexity growth and check their trends. Every one of those is a tractable research program, not a poster on a dorm wall. All of which loops back to our first question with a new sobriety. Why are we here sounded at the outset like a metaphysical riddle answered by because somewhere somehow we had to be. In the informational grammar, it becomes the code word that inflation wrote in our patch, its spectrum of fluctuations, its low energy constants, its horizon area, made a world where free energy persists, where chemistry is rich, where complexity can grow for billions of years. In a larger quantum state, with many code words, observers will overwhelmingly arise in those rare words that permit long computations, long biological histories. That is not destiny, it is conditional probability. It does not close the book, it tells us how to read the next page. We keep asking whether dynamics can shrink the menu of code words, whether symmetry can fix what looks environmental, whether new data push us toward or away from eternal behavior. And perhaps the deepest comfort is practical. Even if the cosmos writes in a sprawling entangled hand our patch is legible, we can measure the faintest polarizations in ancient light, weigh neutrinos by their suppression of small-scale structure, hear space ring to the merger of black holes, and one day perhaps to the hum left by the first fractions of a second, watch the hydrogen fog clear as the first stars ignite, and cross-examine it all against the grammar of quantum fields and gravity. Meaning in such a world is local and handmade. It is the act of decoding carefully, collaboratively, with humility, what the universe has written on our sky. And if that decoding occasionally stutters so does any honest voice thinking aloud in front of something this vast. Let's bring all these threads, inflation's seeds, horizons with heat information as grammar, down onto one workbench and ask a very practical question. How does a finite patch like ours keep time, not clock time on a wrist, but the arrow that runs from simple to structured, from smooth to star-studded? Because if we can see how the arrow is set and maintained, we can understand why there was ever room for life to try, fail, and try again across billions of years. The arrow begins with a paradox that is only apparent. Inflation makes the universe simple, exquisitely smooth, flat, nearly featureless by diluting away wrinkles and flinging relics into irrelevance. In thermodynamic language that sounds like low gravitational entropy. Yet the second law insists that entropy should rise. The resolution is that gravity is mischievous. A smooth mass distribution has less gravitational entropy than a lumpy one, because clumping opens up many more microstates. Inflation then does a curious kindness. It prepares a low gravitational entropy initial state and sprinkles it with tiny quantum-born seeds. After that, gravity does what it does, amplifying those seeds into halos, stars, and galaxies. So entropy grows and the arrow runs forward. The universe becomes interesting not in spite of inflation's smoothing, but because of it. The early calm gives time for complexity to accrue at a measured pace. That measured pace depends on numbers we can name. The amplitude of the primordial fluctuations, the parameter often called I-SE. I-SE sets how quickly the first structures collapse. Too large, and the cosmos would rush headlong into black holes, and starbursts, a fireworks show that ends before chemistry gets its act together. Too small, and everything dawdles with the first galaxies turning on so late and so sparsely that heavy elements and stable planetary systems become rare. Our value sits in a quiet corridor that yields long-lived metal-enriching stellar populations and disks stable enough to shepherd rocky worlds. That's not mysticism, it's engineering. Change the initial ripples and you change the build schedule for everything from dwarf galaxies to the lullabies of climate on temperate worlds. There's a companion number hidden in the neutrino sector. Neutrinos are light but not weightless. Because they move fast in the early universe, they smear out small-scale clumps. The sum of their masses, therefore, tamps down structure on galaxy-building scales. Cosmology weighs them by watching how strongly matter clusters across time. A larger mass sum means slightly less clustering today than you'd expect from the microwave background alone. Laboratory experiments chase the same quarry from the other end, beta decay kinematics and neutrinoless double beta decay searches, and the two approaches are beginning to bracket the truth. The lesson for our arrow is crisp. Even the faintest ghosts in the particle zoo nudge the tempo by which the cosmos composes its symphony. If the setup of the arrow belongs to inflation, the sustain belongs to starlight. Stars are engines that turn gravitational potential into photons and heavy elements, bathing worlds in free energy far from equilibrium. The duration of that sustain depends on nuclear details, resonances like the one that greases the triple alpha route to carbon, the rate of proton fusion that keeps sun-like stars on gentle time scales, the opacity of stellar interiors that regulates convection and stability. Tweak the fine structure constant or the ratio of electron to proton mass, and these balances shift. Once again, you find narrow corridors where the era of gentle stars lasts billions of years. We don't need to imagine why we are in one such corridor to appreciate that living there is what let minds arise. That can even pose the question. So the arrow is not just about forward, it's about long enough. Let me turn to a different facet of time that is at first glance almost cheeky cosmic variance as a clock. On the largest angular scales, we are limited not by instruments, but by the fact we only have one sky, one set of random draws. That limit has a curious property. It tells you how complete your knowledge can be, and therefore how quickly knowledge can grow with better data. For temperature at the lowest multipoles, the answer is not much quicker. For polarization for lensing, for three-dimensional maps of galaxies, the answer is much quicker, because each brings new, independent modes. In a sense, cosmic variance sets a metronome for discovery. It says here the music is already as loud as it can be. Here you can still turn the volume up. Happily, we are turning it up. The Euclid mission is mapping geometry and growth by watching how galaxies cluster and how mass lenses background shapes across billions of light years. The Roman Space Telescope will add a wide, sharp infrared view. Ground-based behemoths, dark energy spectroscopic instrument and colleagues' now larger surveys soon are drawing a three-dimensional atlas of matter. On the microwave side, the next wave of polarization observatories and balloons is stalking the faint curly B modes that a background of primordial gravitational waves would leave. A detection at even a few parts in 1,000 of the scalar amplitude would scream high-energy inflation, filling in the height of the potential. Ever-tightening non-detections would favour lower-lying, quieter hills. Either way, a paragraph of the early universe chapter gets inked rather than penciled. There's another messenger already at the door. Pulsar timing arrays consortia of exquisitely regular cosmic clocks have reported evidence for a nanohertz gravitational wave background. The leading interpretation is a chorus of supermassive black hole binaries, but as the spectral shape clarifies and cross-correlations sharpen, we'll test for any primordial contribution. In the 2030 seconds, a space interferometer will listen in the millihertz band, a range where cosmic phase transitions or features in reheating could have sung. If we eventually stitch together a broadband gravitational wave spectrum from nanohertz to hundreds of hertz, we'll have for the first time a sonogram of the universe's thermal history. It's difficult to overstate how transformative that would be, a second independent channel complementing the photons of the microwave background. All of this precision pushes back on the more flamboyant corners of eternal inflation. If we continue to see a nearly perfect single clock pattern with no isocurvature, tiny non-Gaussianity, and either a modest tensor signal or a very low upper bound, then the class of inflationary potentials that can plausibly go eternal narrows. That doesn't disprove the global picture, it refines the list of scaffolds that could yield it. Conversely, if we found a clear, shape-specific violation of the single clock consistency relations or a robust isocurvature mode that can't be exercised by late-time physics, we'd know the early universe hosted extra light, fields, the kind of ingredient that makes a richly populated landscape more likely. In both directions, measurement is the arbiter. There's a delicate point about predictivity worth revisiting with a cooler head. Critics sometimes say if many low-energy laws are realized somewhere, nothing is predicted, but even ensembles can yield sharp typicality statements. Take the vacuum energy. If a deep theory spreads possible values roughly uniformly across a range much wider than the narrow band compatible with galaxy formation, then observers overwhelmingly measure values near the upper edge of that narrow band, the largest vacuum energy that still lets galaxies condense. Our measured value sits within a couple of orders of magnitude of that edge. That is not a triumphant derivation, it is a statistical nudge. The right response isn't to declare victory, it's to demand more, compute the distribution, specify the selection function, look for correlated typicalities with, say, the fluctuation amplitude, and be explicit about uncertainties. Symmetry first, selection last, and when selection is used, it must be used quantitatively. Because we've been speaking the language of information, let me point to one more frontier, where that language becomes a tool rather than a metaphor, cosmological entanglement as an observable. Long wavelength modes that left the horizon during inflation imprint subtle consistency relations among smaller scale statistics. In the information grammar that's entanglement shaping accessible correlators, upcoming large volume galaxy surveys can test those relations in 3 dimensions with a precision the 2-dimensional microwave sky can't match. A confirmed clean deviation would telegraph extra degrees of freedom at work, and the shape of the deviation would diagnose their type. Theoretically, there is parallel progress, adapting the machinery of quantum extremal surfaces, the same trick that recovers the page curve for black holes to expanding spacetimes. Early results hint that we can in principle compute fine-grained entropies for cosmological radiation and see how information is apportioned between an observer's patch and the rest. Turn that hint into a robust calculation, and measure problem begins to look less like a paradox and more like a question of code and boundary data. What about beginnings in this grammar? The past incompleteness theorems say that eternally inflating spacetimes on average, expanding, cannot be extended backwards forever along all paths. Something like an initial quantum state remains to be specified. 2 famous proposals, no boundary and tunneling, try to do that, weighting classical histories by precise mathematical rules. Each can be asked to compute the likelihood for inflation to begin the expected number of e-folds, even the sign and size of the spectral tilt. Neither has won the day, and both are technically thorny, but they embody the right attitude. Don't swap mathematics for metaphors. Phrase the question so a calculation can in principle return a number. The hope, speculative but not empty, is that a mature, holographically flavoured quantum cosmology will compute probabilities within a patch in a way that never asks you to divide infinity by infinity. Let's not lose the human scale while we juggle these deep pieces. Our patch is finite, our lives are short, our instruments are stubbornly earthbound. And yet the method, patient measurement, married to mathematics, has already told us that the sky's mottling is quantum in origin, that space-time has horizons with heat, that black holes count their bits on their skins, that neutrinos weigh enough to leave a fingerprint in how galaxies grow, that the expansion is accelerating under a vacuum-like pressure. None of that was given to us by birthright. It was earned by detectors sweating on mountaintops, by satellites cooling bolometers, a whisper above absolute zero by pulsar astronomers, cross-checking every tick over decades. Meaning in a multiverse or a single verse is local and made. So where do we walk next? Step by step, without rhetoric. We build the polarization maps that will either hear the primordial tensor hum or force the inflationary potential to sit lower and smoother. We chart the late-time web so precisely that any friction in the growth of structure, be it from neutrinos' warm dark matter or gravity's long-distance quirks, shows its face. We listen across the gravitational wave spectrum for any non-astrophysical backgrounds that point to reheating or phase transitions. We push laboratory neutrino experiments to meet cosmology in the middle. We refine the mathematics that treats a horizon patch as a finite quantum system with a boundary code, and we ask it for identities we can test. And we keep one eye on the quiet philosophical demands of honesty, not to hide behind ensembles when symmetry can do the job, not to mistake clever language for a calculation, not to confuse open horizons with open seas and non-speculation. If eternal inflation is how nature writes, we are living in one of its gentlest chapters, flat, cool, patient. If it is not something equally subtle, waits in the wing. Either way, the arrow that matters to us, the time that allows stars to age elements, to brew planets, to coalesce and minds to notice, was written into the initial conditions and sustained by long-lived, forgiving physics. That is the why available to measurement, not that we were meant to be here, but that this patch makes here a place where long computations are possible. So let's carry that thread into one more domain where patience pays off the first luminous structures. If the quantum seed story is right, the timing, brightness and patchiness of cosmic dawn should follow a score we can predict, and soon, with hydrogen's faint whisper as our guide, we'll be able to listen. Let's walk into the dark, into the long night between the last scattering of light and the first dawn of stars, and ask what precisely it would mean for our inflationary seeds to have written the score for that awakening. Cosmic dawn is not a single moment, it's a slow choreography. Hydrogen cools halos condense the first stars, flicker and die galaxies, stitch themselves from gas and gravity, and slowly the fog of neutral hydrogen thins as ultraviolet light breaks atoms into protons and electrons again. We call that great thinning reionization. If eternal inflation is the overture and the microwave background is the overture's echo, then cosmic dawn is the first act, where notes on the page become music. And our job now is to listen with instruments that can hear that music in the faintest whisper, a spin-flip radio line from hydrogen stretched to meter wavelengths by expansion. A lacing of absorption in the spectra of distant quasars, the flicker of galaxies so faint that only the sharpest infrared eyes can see them. Start with the neutral hydrogen line because it is the most honest of chroniclers. A hydrogen atom left alone lets its electron flip its spin relative to the proton and emits a photon with a wavelength of 21 centimeters. In the expanding universe, that line is redshifted into a wide band of radio frequencies. Observe at a given frequency and you select a cosmic slice, a time, a distance, a stage in the play. The brightness of that line depends on the spin temperature, a thermometer set by collisions, by scattering of ultraviolet photons, and by the cooling and heating of the gas. If the spin temperature is lower than the microwave background at that epoch, hydrogen appears in absorption. If higher, it glows in emission. This is exquisite because it turns the sky into a three-dimensional map. Tilt your dial and you scroll through time. In the earliest part of the night before stars, the gas cools by expansion and gentle collisions keep the spin temperature tied to the gas temperature. Against the still warm microwave background, the hydrogen would in principle appear as a broad, very faint absorption. Then the first stars switch on. Their ultraviolet photons, particularly those just below the Lyman alpha resonance couple, the spin temperature to the gas once more, deepening absorption even as the first X-rays from early black holes and hot stellar remnants begin to warm the medium. Eventually the gas warms above the microwave background and the line swings into emission. Finally, as ionized bubbles percolate and overlap, the neutral signal fades because in ionized regions there is no longer hydrogen to sing. That full arc absorption, warming, emission, silence is the hoped-for symphony of cosmic dawn. Its timing and shape depends sensitively on the small-scale power spectrum, that inflation set on the efficiency of star formation in tiny halos on feedback that can blow gas out of shallow gravitational wells, and on the early population of X-ray sources that turn cold space temperate. There have already been tantalizing hints though, the caution lights blink. A single antenna experiment reported a deep absorption trough at a redshift around 17, corresponding to a time when the universe was only a few percent of its current age deeper than most standard models predicted. To explain it, one must either cool the gas more than expected or brighten the background against which it's seen. Exotic interactions between baryons and dark matter were suggested, as were radio-loud backgrounds from early black holes. But such a bold claim demands careful cross-checks. Independent instruments must confirm the shape, and the foreground treatment must be watertight because the bright galaxy above us is far louder than the cosmic whisper beneath. Arrays designed to map fluctuations rather than measure global averages are pressing ahead. The hydrogen epoch of reionization array and its peers are learning to subtract the smooth, bright foregrounds with surgical precision, so the rippled, fainter 21 centimeter structure can emerge. The square kilometer array, when it comes fully online, will have the sensitivity and resolution to watch the ionized bubbles grow and merge across cosmic volumes to measure their typical sizes, and the patchiness of the reionization front. That patchiness is not poetic, it is a statistic you can compute from the initial spectrum of fluctuations and the astrophysical response. While radio arrays, LISTEN telescopes tuned to the infrared are already seeing the lanterns that lit the fog. The James Webb Space Telescope has pushed the sensors of galaxies to redshifts beyond 10 light leaving, when the universe was a few 100 million years old. Those galaxies are small blue and star-forming. Their ultraviolet output is precisely what carves ionized bubbles in the neutral medium. Measure their abundance and you estimate the photon budget. Measure their spectra and you infer how readily photons escape through dust and gas to ionize the intergalactic medium. There is a balancing act here. If galaxies alone reionize the universe on schedule, then they must be numerous down to very faint luminosities or leak a healthy fraction of their ionizing light. If they are rarer or leak less, then help is needed, perhaps secreting black holes, contributing hard photons, perhaps population 3 stars, those first metal-free giants that burned hot and brief, boosting the early ultraviolet background. Quasars, supermassive black holes feasting in the early universe, offer a different diagnostic. Their spectra, as they pass through the intergalactic medium, acquire a forest of absorption lines from residual neutral hydrogen. At very high redshift, the forest thickens into a near blackout called a Gunn-Peterson trough. The trough's depth and its evolution with redshift are proxy measures of the neutral fraction. Today, the consensus is that reionization was well underway by a redshift of 8 and largely complete by around 6, though perhaps not uniformly. Some regions may have cleared early while others lagged behind. The kinetic Sunyaev-Zeldovich affect tiny temperature fluctuations in the microwave background caused by moving ionized bubbles, scattering photons, adds an integral constraint, too extended. A reionization drags its signature out of bounds. Put these together and you begin to ink the reionization timeline with error bars that will tighten as the 21 centimeter maps switch on. How faithfully does this dawn record the promises of inflation more than you might think? The abundance of the smallest halos that form stars depends on the small-scale end of the primordial power spectrum. Any suppression, say from warm dark matter free streaming or from non-standard initial conditions, would delay the first light and alter the bubble size distribution. Non-Gaussianity, if present at levels beyond current microwave constraints, would modulate the abundance of rare peaks and change the clustering of early sources in measurable ways. Even the sum of neutrino masses leans on the timeline. Heavier neutrinos suppress small-scale clustering, slightly shifting the tempo of the first galaxy's assembly. The dawn is in this sense a second audit of inflation's handwriting written in a different alphabet. There is also the puzzle of the earliest black holes monsters, with masses of hundreds of millions or even billions of suns found within the first billion years. How did they grow so fast? Two broad families of pathways compete. One begins with the remnants of the first stars, tens to hundreds of solar masses, which must then feed voraciously, perhaps aided by super Eddington flows or by repeated mergers in gas-rich environments. The other posits direct collapse under special conditions. A massive gas cloud avoids fragmenting into stars and falls inward, forming a black hole seed of 100,000 solar masses that only needs normal feeding to reach the observed sizes on time. Both pathways are sensitive to the early radiation background and to the metal enrichment of gas, the very things the reionization maps will constrain. Tie down those conditions and you learn not only about early galaxies but about the birth stories of the engines that later sculpt galaxy centers. Reionization is not just a tale of lighting, it is a tale of feedback. The ultraviolet background that clears the fog also heats the intergalactic medium, raising the pressure and making it harder for the smallest halos to accrete and cool gas. Star formation in those halos is quenched or delayed. The faint end of the galaxy luminosity function bends, the photon budget reshuffles. Outflows driven by supernovae can eject gas from shallow wells. Metals once forged change the cooling curves and thus the mass scales at which gas condenses. These are complex local processes, but they leave large-scale statistical signatures that can be compared to models that start from the same inflationary seed. The beauty of the next decade is synthesis. Combine the three-dimensional radio maps with galaxy catalogues, with quasar absorption statistics, with microwave background secondary anisotropies, and the degeneracies between astrophysics and cosmology begin to untangle. There's a deeper, quieter thread running beneath all this measurement. The arrow of time we spoke about becomes visible here as a practical schedule. Inflation set low gravitational entropy and wrote a random field of seeds. Gravity amplified them. Cooling and chemistry took their time. Stars and black holes turned on. Free energy flowed across temperature gradients. Entropy rose. But the pace, the fact that billions of years passed between the first hydrogen atoms and the emergence of civilizations able to build radio arrays to listen back, was set by numbers that are measurable and, crucially, that sit in corridors wide enough for error. There is a kindness in those corridors. If the amplitude of primordial fluctuations had been 10 times larger, the night would have ended too quickly. If 10 times smaller, it might never have ended. If the vacuum energy were 100 times larger, galaxies would have been stunted. If negative and large in magnitude, the universe would have recollapsed. Our dawn sits in the middle of a lane, wide enough to permit history. This is where the multiverse rhetoric, if used at all, must be used with discipline. In a landscape where different patches take on different low-energy code words, observers will not be uniformly distributed. They will cluster in regions where the arrow runs long and gentle. That is a conditional statement, not a proclamation of fate. It does not replace dynamics. It complements it. The dynamics, gravity, cooling, fusion, feedback explain how the dawn proceeds once the numbers are set. The selection statement explains why we might not be surprised to find ourselves in a patch where the numbers land in the life-friendly corridors. And because we are scientists rather than poets, we ask the next questions quantitatively. Can we compute the distribution of parameters in any concrete high-energy framework? Can we make correlated predictions about the vacuum energy and the fluctuation amplitude, for instance? That can be tested statistically as our maps of the dawn mature. That is the standard we should demand of any appeal to many worlds. It must sharpen, not soften the demands of evidence. Meanwhile, the informational grammar we adopted has work to do here as well. The 21 centimeter field is a living record of entanglement patterns, writ large, long mode modulations of small-scale power consistency relations that should hold if a single clock set the script violations that would betray extra light fields in the early universe. Future surveys will measure these relations in 3 dimensions, not just on a 2-dimensional sky. And the notion that a horizon patch is a finite quantum system with a boundary code has a cosmological echo. The light cones of cosmic dawn, the ionized bubbles expanding into neutral gas, a causal diagram. Their growth and overlap can be recast as information percolation through a network with rates set by astrophysical parameters and topology set by the initial spectrum. It is more than a metaphor to say we are watching the universe compute its first luminous structures. If we step back, the path ahead is delightfully concrete. Improve foreground subtraction and calibration to let the 21 centimeter maps break free of the galaxy's glare. Expand galaxy surveys at very high redshift to anchor the photon budget. Use quasar sightlines as needles that thread through the fog, sampling neutral fractions along different lines of sight. Cross-correlate every map with every other map to reduce noise and break degeneracies. Keep tightening the early universe parameters, tilt non-Gaussianity, tensor amplitude, because they are the constraints the dawn must respect. And hold fast to the ethos that has brought cosmology from conjecture to measurement. Don't be seduced by tidy narratives that outrun the data. Don't lose imagination to caution. Let the sky decide at every step. There is a satisfying symmetry in the story we're telling. Quantum jitters, smoothed and stretched by inflation, froze beyond a horizon. Later, as the horizon grew, those numbers thawed into structure. Horizons, with their whisper of heat, tell us that information is counted on surfaces even as structure grows in volumes. The dawn itself is the first great exchange between the two. Light leaking from tiny volumes transforms the vast surface of the universe from opaque to transparent again. And we latecomers under a quiet yellow star can now eavesdrop on that exchange. We can measure the timing of the first notes, the tempo of the warming, the size of the bubbles, the hum of the first black holes. So, when we say the inflationary story is testable, we mean exactly this. It commits to a schedule for the dawn, and we are now in the era when that schedule can be read off the sky. If the schedule holds, the scaffolding stands. If it does not, we'll rebuild, because the night was never empty. It was always full of clues. Let's step through the dawn and into the daylight, the long industrious era, when galaxies settled into spirals and ellipses. Stars arranged themselves along the main sequence, and the chemistry of planets had time to get ambitious. If inflation wrote the overture and reionization struck the first chords the next few billion years, are the symphony's long development themes introduced, transposed and woven together with patience. This is the era that turns a cosmological sketch into places, and it is here that the grand abstractions, vacuum energy, initial fluctuations, neutrino masses, quietly decide the prospects for oceans, atmospheres and mind. Begin with the scaffolding dark matter, halos, each a well in the gravitational landscape. In the standard picture, cold dark matter flows into filaments, finds intersections and tumbles into halos that grow by mergers and slow accretion. Baryons, ordinary matter, ride the same currents, but must shed energy to settle. They radiate, cool and form disks, where angular momentum halts their collapse. Spiral galaxies take shape as rotating plates of gas and stars within halos. Elliptical galaxies arrive when violence merges and instabilities rearranges orbits into a pressure-supported ball. All of this choreography is predicted statistically from the initial power spectrum that inflation left us. Change the small scale slope a little, and you change how many dwarf halos appear. Alter the amplitude a little, and you change when the first Milky Way-sized halos assemble. So, the galaxy population over cosmic time is in truth a readout of the earliest ripples, integrated through gravity's long patience. That readout is now exquisitely detailed. Deep surveys have mapped the star formation history of the universe, a rise from the first billion years to a broad peak around 3 to 4 billion years after the Big Bang, and then a slow decline to the present day. The reasons are physical, not merely poetic. Early gas supplies were plentiful and coolable. Halos were smaller, so fresh accretion could feed star formation efficiently. Feedback from supernovae and active galactic nuclei regulated but did not quench the cosmic furnace. Later, as halos grew, massive gas falling in was shock heated to temperatures that delayed cooling. The universe's expansion stretched filaments thinner. The ultraviolet background maintained by accumulated starlight and quasar-light kept diffuse gas warm. Star formation migrated from universal exuberance to local craftsmanship, spiral arms, combing gas into stars in orderly lanes, while galaxy centers sometimes fell quiet under the watch of supermassive black holes. Those black holes deserve their own paragraph, because they couple the small and the grand in a way that feels almost conspiratorial. Feed a central black hole, and it answers in jets and winds that can reach well beyond the galaxy's heart, heating gas and throttling future star formation. The observed correlation between black hole mass and the velocity dispersion of stars in the galactic bulge suggests a feedback loop. Galaxies and their black holes evolved together, negotiating a balance. Where did the seeds come from? We touched on the fork remnants of the first stars versus direct collapse. But the later growth is written in the language of supply lines, cold streams of gas along filaments mergers that deliver fresh fuel, and in the timing set by the halo's assembly history. Inflation's numbers filtered through structure formation decide how many such supply lines reach a halo like ours, and when. Now, if you want to talk about habitability without romance, you talk metal. Not the music though, the soundtrack is grand, but the astrophysical metals, all elements heavier than helium. Planets, especially rocky ones, are built from metals. Atmospheres rely on volatiles that themselves are forged in stars and supernovae. The universe began with hydrogen and helium, a pinch of lithium and beryllium. Everything else is stellar afterthought. The metallicity of gas rises over time as generations of stars live, die, and expel enriched material. Spiral galaxies, where star formation persists, gently build up metals in their disks. The inner parts of those disks become especially rich. There is a Goldilocks zone in chemistry, just as there is in temperature. Too few metals, and you struggle to assemble rocky planets. Too many, and you risk rapid dust formation that can accelerate cooling and star formation in violent short bursts that destabilize planetary environment. Our sun's composition, modestly metal-rich compared to ancient stars, sits in a corridor that seems to favor complex planets with long, stable epochs. The dance of a planet around its star is then choreographed by stellar physics. A main sequence star like the Sun brightens slowly over billions of years as helium ash accumulates in its core and the nuclear furnace adjusts. That steady brightening moves the classical habitable zone, the annulus where liquid water can persist on a rocky surface outwards over time. Planets, for their part, negotiate with geology and magnetism. Plate tectonics recycles carbon between rocks and atmosphere, stabilizing climate through feedback. A magnetic field shields the surface from stellar winds and helps a planet hold on to its atmosphere. None of these features are universal. They are outcomes of mass composition, heat flow and chance. Yet they are all downstream of cosmic bookkeeping, the distribution of elements, the star's stability, the quiet of the local galactic environment. The point is not that cosmology explains life. It is that cosmology sets the priors, the broad constraints within which biology can tinker. Here's a subtle cosmological prior that rarely gets airtime: dynamical serenity. A galaxy's neighborhood matters. Sit near a crowd of massive neighbors and tidal forces can stir the gas trigger bursts of star formation or fling comets from distant reservoirs into the inner system too often for comfort. Live in a lonely backwater and the supply of fresh, low metallicity gas dwindles, starving new star formation. The Milky Way sits in a mild suburb, tight enough to have a companion in Andromeda and a retinue of dwarfs, but not so tight that our disk is constantly harassed. Even within the disk, the Sun seems to circle on a path that avoids frequent plunges through spiral arm's densest star-forming regions, lowering the rate of nearby supernovae that could sterilize surfaces or strip atmospheres. These are probabilistic comforts, not guarantees. But they are the sorts of comforts that a universe with our measured parameters supplies in some fraction of its galaxies at some epochs again, because inflation and its offspring set the large-scale architecture that decides how galaxies live. A multiverse story, if we choose to tell it, would say in regions where the fluctuation, amplitude or vacuum energy fall far from our measured values, the galaxy demographics and halo assembly histories will shift. Perhaps there are bubbles in which most halos assemble too late, others in which the vacuum energy strangles structure early, others where neutrinos are heavy enough to damp small scales so thoroughly that disks have trouble settling. Observers, by which we mean long-lived chemical computations capable of noticing, would cluster in the corridors where halos assemble on schedules compatible with metallurgy and where stellar lifetimes are long and gentle. That rhetoric can drift into hand-waving if we let it. The antidote is to compute typicalities in a concrete theory where parameters vary derive the distribution of galaxy histories, define observer windows operationally timed to produce heavy elements, fraction of stars quieter than a given variability, stability of planetary orbits in disks of a given environment, and ask where those windows overlap. The result would be a statistical atlas of habitability across parameter space, not a just so tale. Meanwhile, our telescopes don't wait for philosophical closure. We are counting exoplanets by the thousand, reading their atmospheres by transit spectroscopy, and beginning to measure demographics, how planet occurrence depends on stellar mass and metallicity, how architecture depends on disk history. The early returns are thrillingly messy. Super-Earths and mini-Neptunes crowd the close-in orbits around many stars, a class of worlds absent from our solar system. Hot Jupiters, once a surprise, are now a recognized subpopulation giant planets that migrated inward through disks or through dynamical jostling. Multi-planet systems often show near-resonant chains, fossil records of migration in dissipative gas. All of this complexity sits atop the prior's cosmology set, which stars formed when, with what compositions, in what environments. In the next decades, direct imaging missions will aim for reflected light from Earth-sized planets around Sun-like stars seeking biosignature gases. If we are fortunate, we will move from an existence-proof life here to a distribution life across many. And that distribution will be another map we can try to explain in the language of initial conditions and long physics. There's an aesthetic pleasure in noticing how many arrows point the same way. Inflation smoothed the universe and planted quantum seeds. Gravity amplified those seeds into a web. Baryons cooled and settled into disks within halos, forging stars that brewed metals. Planets condensed from dust atmospheres formed and sometimes endured, and on at least one world, chemistry found the trick of heredity and metabolism. Each stage used what the previous stage handed down. And at each stage, numbers mattered. The fluctuation amplitude had to be in a corridor, the vacuum energy had to be small and positive, the fine structure constant and electron to proton mass ratio had to sit where stellar interiors are stable and chemistry rich. The neutrino masses had to be small enough not to smear away too much structure. None of these numbers need be explained by a single hand. Some may be fixed by symmetries we've yet to uncover. Others may vary across a landscape and be filtered by selection effect. The honest position is to work both angles symmetry first, when symmetry fails to fix selection last, and always quantitatively. What of time's far future? If the vacuum energy is truly constant, our local group will gravitationally bind and merge into a single massive galaxy, as more distant systems slip over our horizon, their light redshifting into invisibility. The night sky will thin not because the stars go out immediately, but because the stage grows lonely as expansion fences off the rest of the play. Stars will age, the metal ledger will close, black dwarfs and faint embers will dominate. On fantastically longer timescales, even black holes evaporate their information, trickling out in Hawking radiation. It's a melancholy picture, but not a nihilistic one. Information is not destroyed. It is diluted, dispersed across horizons and quanta. If eternal inflation is the global script, other chapters continue elsewhere, but those are not ours to read. The meaning in our patch, across the billions of years we were granted, is local, to measure, to understand, to build, to pass knowledge on. The scale of the stage is immense, the script we can read is finite, the combination is strangely humane. All this talk of scales and schedules can sound cold until you realize what it implies about us. The initial conditions and laws did not write people into the universe. They wrote patience, smoothness, and seeds. They wrote the possibility of long computations carried out by starlight, far from equilibrium. Everything else, galaxies, planets, life, mind, was emergent, contingent, the result of chance filtered through selection and stabilized by feedback. In a very literal sense, we are the universe remembering its own quantum childhood. The pattern in the microwave background, the mottled record of fluctuations frozen when the first atoms formed, was the first page of a diary written in statistics. The chemical complexity on a living world is another page written in enzymes and errors. The telescope, the particle detector, the equation on a chalkboard, the signal process from a pulsar's ticks, these are the later entries where the diary becomes self-aware. So where does this leave the question? We started with why are we here? The rigorous answer we've assembled is spare and satisfying. Because inflation, or something like it, prepared a low entropy stage with tiny, nearly scale invariant seeds. Because the numbers vacuum energy fluctuation, amplitude coupling constants fell in corridors where structure grew gently and stars lived for billions of years. Because the galaxy we inhabit assembled calmly. Because our star is steady. Because our planet kept its atmosphere and cycled its carbon. None of that is destiny. All of it is physics. In a single universe view, some numbers will have deep dynamical explanations we've yet to discover. In a multiverse view, others may be environmental and then filtered by selection. The honest route is to keep both possibilities on the bench test, the scaffolding that leads to either, and let the sky continue to grade our homework. There is one more bridge worth crossing because it connects explanation to experience. When you stand under a truly dark sky and see the Milky Way as a pale seam running from horizon to horizon, you are looking at a fossil of all the processes we've described: inflation's ripples, gravity's growth, stellar alchemy, planetary odds and ends. The light reaching your eyes left its stars long before any human language was spoken. It carries no message intended for us. It is not a sign. And yet by doing the work, by building instruments, by arguing about models, by being skeptical and precise, we have learned to read that light as if it were a script. We can tell when those stars formed, how the gas flowed, what the dark matter must be doing, and how the earliest quantum whispers set the rhythm. That act of reading is, I think, the closest thing to meaning that physics offers. So we keep reading, and we are not done. The measurements we've discussed, the 21 centimeter maps of the dawn, the polarization swirls that would betray primordial gravitational waves, the precision charts of galaxy growth and lensing the whispers of gravitational wave backgrounds are not luxuries. They are the exact experiments that can confirm or revise the scaffolding that got us here. If the data continue to favor a single clock, nearly Gaussian, nearly scale invariant seed field, then the conservative corner of inflation grows more secure, and the case for eternal variance becomes a question of particular potentials and measures. If instead we find crisp, reproducible deviations, shape-specific non-Gaussianity, isocurvature, unexpected small-scale suppression or enhancement, then we will know that the early universe's pen had more than one nib. Either way, the story sharpens. So let's end this movement where the day truly begins with a small, rocky world under a quiet star, bathed in photons, forged in a core where protons tunnel and fuse. On that world, oceans cycle heat and salt, continents drift and collide, a thin gas envelope scatters blue and glows red at the edges of day. Somewhere in that envelope, a radio antenna points up to listen for the softest echo of the first stars, while a cryostat keeps a bolometer at a fraction of a degree above absolute zero to catch ancient polarization. Those are the instruments of a species that learned how to turn curiosity into numbers. And that, more than any multiverse flourish, is the gift our patch gave us time to learn. So we honor it by measuring well, by thinking clearly, and by allowing wonder, discipline, truthful wonder, to keep the beat while the universe plays on. Let's turn the lens toward the questions that remain stubborn, the places where the sky's answers are still half-formed, and use them as a map for what to do next. Cosmology is not just a list of solved problems with a misty multiverse painted behind it. It's a living set of tensions, small discrepancies in growth oddities on the tiniest galactic scales, hints from early galaxies that might be asking us to tune the astrophysics, or if we're lucky to refine the early universe script itself. If inflation wrote the overture and galaxies played the symphony, these tensions are the notes that don't quite fit the chord. And that's where discovery likes to hide. Start close to home in theory space, slow roll inflation. The mathematics packages the whole story into two gentle parameters, often called epsilon and eta, that describe the slope and curvature of the inflaton's potential. The hillside, the field rolls down. From those come crisp predictions, a scalar spectral index just shy of 1, a tiny red tilt, very small non-Gaussianity for simple single-field models, and a tensor to scalar ratio that depends on how far the field travelled in its potential. Observationally, that's exactly the pattern the sky prefers so far. A tilt a hair, less than 1 non-Gaussianity, consistent with 0 within current errors, and no firm detection of primordial gravitational waves yet. It sounds tidy, almost suspiciously tidy, but tidy isn't trivial. It means that any deviation, we do detect an anomalous 3-point function with a distinctive shape, a surprise bump in the power spectrum, on some range of scales, a whisper of tensors with a spectral slope that doesn't match the simplest expectations will point like an arrow at which piece of the inflaton's story needs rewriting. The more precisely we write down nothing happened, the louder any something did will sound. Now zoom from equations to galaxies and to the bits that keep theorists and observers at the coffee machine. On very small scales, inside dwarf galaxies along the edges of thin disks, cold dark matter's clean predictions sometimes rub against the messy reality shaped by baryons, feedback and measurement limits. The core cusp tension asks whether the innermost density of dark matter halos should be steeper cusp or flatter core. Pure N-body simulations of cold dark matter prefer cusps. Some dwarfs look cored. The too big to fail puzzle wonders why the most massive subhalos predicted around galaxies like the Milky Way don't seem to host bright dwarfs in the numbers we naively expect. Over the last decade, careful modelling has shown how supernova feedback star formation bursts and tidal effects can flatten cusps and dim satellites. In other words, the messy, luminous physics can reconcile much of the tension. But I think it's fair to say without melodrama that the case is not closed. This is useful. It tells us where new high-resolution surveys and tailored simulations should push gas kinematics in the faintest dwarfs, proper motions that reveal tides, resolved star formation histories that calibrate feedback. Why harp on dwarf galaxies in a grand talk about eternal inflation? Because the early universe seed spectrum is the blueprint from which even the tiny things are built. If, after all the honest baryonic work is done, we still find a statistically robust departure from cold dark matter expectations, then one natural lever is the small-scale end of the primordial power spectrum. Warm dark matter, for example, would erase some tiny seeds. A small controlled non-Gaussianity could tweak the abundance of rare peaks. An inflationary feature, a brief pause or wiggle in the potential, could leave a telltale ripple confined to certain scales. The connection is direct. Small galaxies are the magnifying glasses for the earliest quantum scribbles. Push your gaze farther and earlier. The James Webb Space Telescope has opened windows into the universe's first few 100 million years, reporting surprisingly bright, compact galaxies at redshifts beyond 10. Some inferred stellar masses and star formation rates looked at first pass alarmingly high for so early an epoch. Are we seeing genuinely rapid stellar assembly, or are dust emission lines and lensing tricking our estimates? The balance is shifting as spectroscopic confirmations accumulate and models mature. My take is cautious optimism. It's likely we're learning that star formation can be efficient in some early halos, that initial mass functions and feedback may differ in metal-poor conditions, and that the universe, while not breaking its own rules, has more imagination than our simple priors. And if after the dust settles quite literally, we still read a story that strains the standard seed spectrum, that would be thrilling. It would send us back to the inflaton's hillside to consider small, physically motivated features, a kink, a step, a transient period of faster roll. So the right attitude is neither denial nor hype, it's to invite the data to corner us. Alongside these astrophysical fronts, there's a more austere tension in the late-time growth of structure. Some weak lensing surveys have reported slightly less clumping than you'd expect when you extrapolate from the microwave background under the simplest model of gravity and dark energy. The word slightly matters. Systematics are hard and cross-checks are everything. But even a mild, persistent shortfall, if it survives, better calibrations has sharp forks, perhaps neutrinos are a bit heavier, perhaps dark energy has a whisper of time, dependence. Perhaps gravity is modified very gently on cosmic scales. Each fork feeds back upstream. Heavier neutrinos change the amplitude and timing of small-scale structure, and thus the details of reionization. Evolving dark energy reshuffles the conversion between redshift and distance and affects the precise reading of acoustic rulers. Modified gravity asks whether the inflationary seeds grew under exactly Einstein's rules. If you enjoy detective stories, this is one. The subplots converge. Back at the beginning, there's the quiet elephant in the room. What is the inflaton? We've been quite comfortable describing its behavior without pinning down its identity. As normal fluids were understood thermodynamically before molecules were discovered, electricity was mapped before electrons were isolated. Still, one day we'd like a derivation instead of a description. High energy theories, supersymmetry, extra dimensions, axion-like fields supply candidates with potentials that are radiatively stable, protected by symmetries. Those symmetries often encourage very small non-Gaussianities and low tensor amplitudes, conspicuously consistent with what we've seen so far. But if the data ever point to a high tensor to scalar ratio, attention will swing toward large field models with specific signatures. If we see equilateral type non-Gaussianity, we'll know interactions were strong enough that the inflaton's sound speed dipped below light, a very different microphysics. The game is beautifully constrained, just a few numbers, tilt, non-Gaussianity shape, and size, tensor, amplitude stand as lighthouses guiding us back to ultraviolet shores. While we wait for the sea to part, we can do something wonderfully terrestrial, build better instruments and smarter analyses. Microwave polarization is the crown jewel. The curl-like B modes that a primordial gravitational wave background would imprint are faint vulnerable to galactic dust and to lensing distortions that convert other modes into curls. The community's answer is surgical multi-frequency maps that separate dust by its spectrum, delensing where we use maps of the intervening mass to subtract lensing's twists and uncover the primordial pattern beneath. It is a tour de force of statistics and experimental craft. A tensor to scalar ratio at or above a few parts in 1,000 would be a discovery, marching the upper limit below, that will still disqualify broad families of potentials and weigh on the plausibility of eternal behaviour in some classes of models. Either way, the question tightens. Parallel to that, the 21-centimetre frontier will start turning from pathfinder to cartography. Foreground's galactic synchrotron and free emission are orders of magnitude brighter than the cosmological signal, but they are spectrally smooth. The cosmological fluctuations wiggle in frequency. That difference is our lever. Intense effort on calibration beam chromaticity and foreground subtraction is turning a wall of glare into a partly transparent curtain. Once the maps are secure, cross-correlate them with galaxy surveys and CMB lensing. Correlations lift signals out of noise and break degeneracies between astrophysical parameters, escape fractions, X-ray heating, and cosmological ones, small-scale power neutrino mass. It's the old trick of physics triangulate. I want to put a spotlight on neutrinos again because they are so shy and yet so talkative in aggregate. The sum of their masses suppresses small-scale clustering. The way that suppression appears across redshift and scale is now a precision observable. Cosmology is already setting upper limits competitive with lab experiments. If both avenues converge on a narrow value, it will be one of the loveliest cross-checks in science. Ghostly particles weighed by the scaffolding of galaxies and by beta decay kinematics in tabletop instruments. And if a small discrepancy appears cosmology a touch lower or higher than the lab, it will tug threads into early times. The web is tight by design. There's another arena where patience could pay disproportionate dividends, stochastic gravitational wave backgrounds beyond the CMB band. Pulsar timing arrays have likely heard a low-frequency background from supermassive black hole binaries a triumph in its own right. Space-based interferometers will open the millihertz band, perfect for any cosmic phase transitions with energy scales and couplings that light up there, and for features from reheating if nature is generous. Ground-based detectors listen at higher frequencies where violent astrophysics dominates, but even there, an unexpected smooth broadband hum could hint at new early universe physics. Imagine confirming an inflationary origin for density fluctuations in the microwave sky and separately reading a relic gravitational spectrum from reheating. 2 sensors, 2 messengers, 1 story. That would be a kind of closure we rarely get. Through all this, we should keep a watchful eye on the multiverse rhetoric. It's tempting when a small number looks odd to reach early, for it varies across bubbles. Sometimes that will be the right diagnosis, sometimes it will be a way of closing a case we should keep open. The discipline I keep returning to is simple symmetry first, selection last. Ask whether a deeper principle can fix the value. Ask whether small departures from the standard model of inflation can account for the data without invoking ensembles. And only then, if a parameter is genuinely environmental in a well-defined high-energy framework, use selection, but use it quantitatively with distributions and correlated predictions. Otherwise, the multiverse becomes a solvent that dissolves curiosity. Used properly, it is not a surrender. It's a statistical lens for parameters that dynamics declines to fix. We should also talk frankly about beginnings and boundaries, because even the best early universe data won't tell us what happened before inflation, if before is a word without meaning in that regime. The past incompleteness theorems keep their quiet pressure on every model that expands on average. You must specify an initial quantum state. Competing proposals try to do exactly that with mathematics. You can, in principle, test indirectly compute the probability of different numbers of e-folds, of curvature, of fluctuation amplitudes, see whether the predictions align with the observed lack of curvature and with the measured tilt. These are hard calculations in a domain where geometry is quantum, not classical. But they're not poetry, they're integrals, and that's heartening. It means even our most rarefied questions are in spirit continuous, with the same habit of mind that weighed the electron and timed the pulsar. Pull back for a moment and notice something quietly uplifting. We began with a blunt question, why are we here? And followed it through inflation horizons, information, dawn galaxies, and habitability. Each step made the answer less mystical and more precise. We are here because the initial conditions were smooth and seeded gently, because long-lived stars had time to brew metals, because vacuum energy is tiny and positive, because the fluctuation amplitude sits in a calm corridor, because gravity, chemistry, and time did their work, because our patch is large and old enough to allow long computations to run. In a single universe picture, many of those facts await deeper dynamical explanations. In a multiverse picture, some may be environmental, filtered by selection. Either way, you can test the scaffolding that leads to either interpretation, and that to me is the same definition of meaning in physics, not an answer that quiets curiosity, but a program that tells you exactly what to do next, which is in fact where we'll go. We have one more bridge to cross that loops us back to the first principles and forward into the lab, the nature of dark matter itself, and the way its identity, cold, warm, self-interacting axionic threads all the way from inflation, seeds to the present-day choreography of galaxies. If the tiniest scales are where the earliest quantum scribbles are magnified, then choosing the right dark matter candidate is choosing the lens. So let's pick up that lens next, examine what each candidate means for the seed spectrum, for reionization's timing, for dwarf galaxy anatomy, and for the experiments on Earth that might at last let us hold a piece of the dark in our hands. Dark matter then, the silent scaffolding. We've been leaning on it all along, letting it hold up filaments, funnel, gas cradle disks without asking squarely what it is. If inflation wrote the initial ripples and gravity did, the amplifying dark matter chose the rhythm section. Change the player and the groove shifts from the timing of cosmic dawn to the anatomy of the faintest dwarf galaxies. So, let's put the candidates on the bench and see how each rewrites the score, then follow the thread all the way to the laboratories and detectors that might finally let us catch the culprit in the act. Begin with the conservative favourite cold, collisionless dark matter. Cold means the particles move slowly compared to the speed of light by the time structures began to form. Collisionless means they interact feebly with themselves and with ordinary matter, apart from gravity. In this picture, every tiny ripple in the primordial power spectrum survives to seed structure, from the grand filaments down to minuscule halos 1,000,000 or billion times less massive than the Milky Way. The hierarchy is clean. Small things form first and merge into bigger things. On large scales, tens to hundreds of millions of light years, this model sings in tune with observations, galaxy clustering, weak lensing, baryon and acoustic oscillations. On smaller scales, the song becomes complex. because baryons take the lead feedback from supernovae puffs out gas. Black holes blow winds, tides stir and strip. When dwarfs display cores instead of cusps, we can plausibly credit repeated star formation bursts with shaking the central potential and flattening the dark matter. The point isn't that cold dark matter is perfect, it's that with honest astrophysics, it remains resilient. But physics advances by listening for wrong notes. If after careful modelling, we found a hard floor to small-scale structure, a genuine absence of halos, below a particular mass, cold and collisionless, would be in trouble. Enter warm, dark matter. Warmth means the particles were still zipping around in the early universe with enough speed to smear out the tiniest ripples through free streaming. The effect in Fourier space is a cut-off modes below a characteristic scale are suppressed. In real space, that means fewer small halos delayed formation of the first galaxies and larger, smoother dark matter cores in dwarfs, even before baryons stir the pot. Cosmic dawn would respond, radio maps of the 21 centimeter line would reveal a later, perhaps more gradual ignition. The bubble size distribution during reionization would tilt toward larger typical scales because the sources are rarer and more clustered. There are already tight constraints. Too much suppression would erase the Lyman alpha forest structure seen in quasar spectra, but a little warmth remains viable. The dawn and the faintest galaxies are precisely where the remaining room can be measured. A different twist keeps the particles cold, but lets them talk to each other, self-interacting dark matter. Give the dark sector a new force felt only by dark matter, and halos become less violent in their centers. Particle orbits exchange momentum, heat flows from the outer halo inward, and cusps relax into cores without help from supernovae. The effect is mass-dependent dwarfs, with their shallow wells core out strongly, clusters with deep potentials core modestly. If the interaction strength depends on relative velocity, as it would for a force with a finite mediator mass, the trend can be tuned to match a broad swath of systems. The cosmos offers laboratories at every scale: dwarf kinematics, galaxy cluster, strong lensing maps, even the offsets of dark and luminous matter in colliding clusters. Meanwhile, the early universe takes note. Self-interactions can alter halo concentration and merger histories, nudging the timing of the first stars and black holes. If inflation's seed spectrum is the same but the dark physics massages the growth, you must disentangle the two with multiple probes, dawn, dwarfs and lenses, until a single interaction strength explains all three. Then there's a beautifully different idea: axions, and their cousins ultralight bosons born as fields more than as particles. If the mass is fantastically small, the de Broglie wavelength can be kiloparsecs across in galaxies. Quantum pressure opposes collapse below that scale, ironing out small structure. On large scales, the model behaves like cold dark matter. On small scales, it behaves like a fluid with a minimum coherence length. The halos that form have chord inner profiles set by the particle mass, and interference patterns can produce delicate, wavy density structures, soliton-like cores with fringes. Cosmic dawn would feel the delay in small halo formation. Pulsar, timing and stellar. Stream experiments might even sense the granular wave interference if nature is kind. The beauty of this candidate is that it can be searched for in the lab by coaxing axion-like fields to convert into photons in magnetic cavities, or by looking for wobbles in atomic transitions if the field oscillates. The astrophysical and laboratory stories meet in the mass parameter. A detection in one domain would set a scale that must explain the cause of dwarfs and the timing of first light. There's a grand romance in the possibility that the early universe wrote not just one dark matter candidate, but a whole dark sector, multiple particles, dark radiation, dark forces. In such a world, the seeds from inflation grow under rules that shift subtly with time. Early self-interactions smooth small structure. Later decays feed relativistic species that leave imprints on the expansion history. Dark radiation alters the precise phase of acoustic oscillations in the microwave background and the galaxy power spectrum. The discipline here is to insist on coherence. The same parameters must thread consistently through relic abundance calculations, structure formation, and precision cosmology. The more knobs, the more chances to cheat. The antidote is over, constraining with many data sets. The reward, if it's real, would be the thrill of uncovering a hidden ecology rather than a single species. Every one of these identities feeds back to reionization in calculable ways. Warmth or wave-like pressure delays the faintest galaxies, shifts the trough and crest of the 21 centimeter global signal and changes the angular power spectrum of brightness fluctuation. Self-interactions reshape halo concentration, changing star formation efficiencies at fixed mass, and with them the timing and patchiness of the ionization front. Even the emergence of the earliest black holes, the seeds of the bright quasars we found less than 1 billion years after the Big Bang, depends on how quickly gas can settle into small halos and whether mergers are frequent. Direct collapse scenarios prefer smooth inflows, a strong ultraviolet background to suppress fragmentation, and rapid assembly conditions tied to both the seed spectrum and the identity of the dark matter. So when we say dark matter affects habitability, we don't mean by magic. We mean by setting the schedule for metallurgy and the calmness of dis. What then do we do to catch the dark on Earth and in orbit? 3 classical avenues run in parallel. Direct detection aims to feel the tap of a passing dark matter particle in an ultra-quiet detector deep underground. For heavy, weakly interacting candidates, the tap is a nuclear recoil. For lighter candidates, the taps might be electron recoils, phonons, or collective excitations in new target materials. Null results have carved away huge swathes of parameter space, pushing cross-section limits to astonishingly small values. Indirect detection watches the sky for byproducts, gamma rays, antimatter that could be produced if dark matter annihilates or decays in dense regions like galactic centers or dwarf spheroidals. Here, astrophysical backgrounds are lively. Caution is vital. Collider searches finally try to make dark matter in high-energy collisions and infer its presence from missing momentum balanced against visible debris. So far, the detectors are patient and the universe is shy. Axion searches are their own art. Microwave cavities in strong magnetic fields scan frequency by frequency for a telltale buildup of photons as an axion field converts. New concepts, dielectric haloscopes, nuclear magnetic resonance-like techniques, dish antennas, extend the hunt across orders of magnitude in mass. Atomic clocks and interferometers listen for oscillations in fundamental constants if the field sways. These are exquisitely sensitive, tunable experiments, and their virtue is that a positive tone would set a mass we could carry straight back to dwarf cores and 21 centimeter timeline. The loop would close laboratory galaxy and dawn would agree, or they wouldn't, and we'd learn which story broke. Cosmology itself is a dark matter experiment done with the largest apparatus ever built. The Lyman alpha forest, the thicket of absorption lines in quasar spectra, maps the small-scale matter distribution at redshifts 2 to 5 and already rules out 2 warm versions of dark matter. Strong lensing time delays and Einstein rings dissect the substructure in galaxy halos. A deficit of small clumps in lens models would whisper warmth or wave pressure. Stellar streams in the Milky Way, those tidal ribbons torn from globular clusters, are perturbed by passing dark clumps. Their gaps and kinks are a seismograph for the halo's granularity. And the 21 centimeter surveys we've discussed will time the ignition of the first sources, putting a clock on the minimum halo masses that could form stars. Each of these probes folds astrophysics in, but together they triangulate with vicious efficiency. Thread the multiverse cautiously through this. If different bubbles host different low-energy physics, some will have warm or wavy dark matter, some cold and collisionless, some with self-interaction. The galaxy population over time, the reionization schedule, the anatomy of dwarfs. These would differ statistically across patches. Observers that arise late in cosmic calendars would cluster where structure grows early enough but not too violently, where disks are stable, where metallicity reaches the right range. It's a seductive story. It can also be a lullaby. The standard remains, do the statistics. In a concrete, high-energy framework where the dark sector can vary, compute the distribution of dark matter identities, propagate them into distributions of galaxy histories, and ask whether any correlated typicalities are robust. If a landscape can predict not just we exist, but it's typical to see, say, a modest suppression of small-scale power and a certain reionization timing, then we have something testable. Otherwise, selection is scenery, not script. There's a deeper link back to inflation because the two are not really separable. The dark matter candidate often arrives with an origin story in the early universe, freeze out from the thermal plasma for heavy, weakly interacting particles, freeze in for feeble couplings, misalignment production for axion-like fields, phase transitions that leave relics or late decays that feed warm components. The abundance and the primordial velocities are not arbitrary dials. They are outputs of the same expansion history that stretched quantum fluctuations across the sky. The trick and the opportunity is to insist on one continuous narrative, choose a candidate, choose its production mechanism, calculate the abundance and velocity distribution propagate through structure formation to dawn and dwarfs, and ask the lab what cross-sections and masses are still allowed. When the story fails at any stage, you rewrite not with adjectives but with equations. I think this is the quiet beauty of where cosmology has arrived. The question, why are we here, led us to inflation to horizons, with heat to information as grammar. Now it leads us almost inevitably to engineering which dark lens is nature using to project the quantum seeds into the galaxies we see. The answer will not only settle small-scale puzzles, it will set the conditions for the first stars, the first planets, and the long patient biology that followed. So we are building the instrument's polarization telescopes to hear inflation's gravitational hum, radio arrays to watch the fog clear, spectrographs to weigh the small-scale power by the flicker of distant quasars, underground ears and magnetic cavities to listen for the dark itself. It's all one project in the end, to turn curiosity into numbers and let those numbers tell us which of the possible universes ours actually is. And perhaps that is the most human way to close today's loop on the dark, not with a flourish, but with a to-do list written in starlight. We calibrate until the foregrounds give way, we delens until the curls are honest, we simulate until baryons stop surprising us. We widen the parameter space of our detectors until modest couplings and light masses have nowhere to hide. The cosmos will answer in its own time, it always does. The job for us is to keep the conversation going, to let each null result be a tightening chord, each anomaly a new motif. And to remember that under a quiet yellow star, we have the leisure to listen carefully while the universe keeps playing. Dark energy now steps onto the stage, the smooth, persistent pressure that makes the expansion of space accelerate, and it is in many ways the strangest actor we've met. If dark matter chose the rhythm section, dark energy sets the tempo for the whole piece. Change it, and the melody of structure growth, the phrasing of cosmic history, the very horizon of what can ever be known will shift. The conservative reading is that dark energy is a true cosmological constant, an energy of empty space that remains the same everywhere and everywhen, with an equation of state parameter, W equals mides, watt equals -1 watt equals mites 1. Modest though that single number looks, it rewrites forever. A constant vacuum energy means the expansion asymptotes to a de Sitter phase, distant galaxies slip over the horizon, the observable stage grows lonelier even as local physics remains warm with stars for a time. So the long forecast is quiet, not an apocalypse, but a fade into sparsity. But we must earn even that quiet. The practical program is to measure whether WWW really equals -1 and whether it stays there. If it wiggles with time, if a light scalar field quintessence slowly rolls down a potential, then the geometry growth relation that ties distances to clustering will deviate from the cosmological constant script. That's why we combine standard candles, supernovae standard rulers, baryon acoustic oscillations, weak lensing, and redshift space distortions. Distances tell us the expansion, growth tells us how matter clumps in response to gravity under that expansion. The two are connected in general relativity. A mismatch says either dark energy evolves or gravity itself is different on large scales, and gravity might be. It's a sober possibility to entertain, because general relativity, magnificent as it is, has not been tested on gigaparsec scales with the same surgical precision as in the solar system or around black holes. Modified gravity frameworks, scalar tensor theories, massive gravity, Horndeski-like Lagrangians can mimic a cosmological constant in the background expansion, while subtly altering how structures grow and how light is deflected. They operate with a delicate etiquette called screening on small scales they hide, reducing to Einstein's theory to pass local tests. On vast scales, they speak changing the relation between potentials that lens light and those that drive matter. Observationally, that means a necessary cross-questioning, do galaxy motions, weak lensing shear, and the integrated Sachs-Wolf effect all sing the same tune, if not the culprit could be evolving dark energy or a gravity. Edit. Distinguishing the two is precisely why upcoming surveys insist on redundant probes over huge volumes. While we're tidying the late-time ledger, we should face the two headline tensions honestly. First, the Hubble tension local distance ladder measurements of the current expansion rate come in higher than the rate inferred by projecting the microwave background forward under the standard model. This is not a quibble over the second decimal place. It's a coherent percent-level discrepancy that has survived many checks. Explanations span three continents of thought. One says astrophysics subtle systematics in supernova calibration. or Cepheid anchors. Another says early time physics tweaked the pre-recombination energy budget, an epoch of early dark energy, for instance, so the sound horizon is smaller and late time distances recalibrate upward. A third says late time physics mild departures from W equals minus 1 watt equals negative 1 watt equals minus 1, or gentle modifications of gravity. Each route has consequences elsewhere. Early time fixes tug the acoustic rulers and nucleosynthesis. Late time fixes nudge the growth of structure and lensing. The discipline is to keep all the plates spinning, no adjustment is allowed to fix one number and break three others. Second, the S8S, 8S8 or growth tension. Some weak lensing surveys have hinted at slightly less clumpy matter than the microwave background anchored model predicts today. Slightly matters. These measurements are hard and pipelines mature. But if a shortfall persists, the branches are familiar, perhaps neutrinos are a touch heavier. Suppressing growth, perhaps dark energy evolves, changing the growth history. Perhaps gravity departs minutely from Einstein at long distances. None of these possibilities is a free lunch. Heavier neutrinos shift the dawn's timeline. Evolving dark energy changes distance, redshift relations. Modified gravity must pass screening tests in galaxies and clusters. So the game is a web again. Pull on one thread, watch the whole tapestry move. It's tempting at this point to lift a different tool out of the box and ask whether some anomalies on small scales point toward no dark matter at all, toward modified dynamics rather than missing mass. Empirically, there is an eerie regularity in galaxy rotation curves. The relation between observed baryonic mass and acceleration follows a tight law over many systems. And some modified dynamics ideas were crafted to encode precisely that. But the cosmic jury is broader than this. The microwave background's acoustic peaks, the pattern of large-scale clustering, the lensing of light by structures with very little baryonic content. The bullet cluster's offset of mass and plasma, together they speak with a nearly unanimous voice for a dark matter component. Modified dynamics can recover pieces of the song locally. The full symphony, for now, still prefers a dark, gravitationally bound player. The honest stance is to keep listening to use those very baryonic regularities as calibration challenges for galaxy formation inside a dark halo, and in parallel to keep modified gravity on the bench as an organizing principle for precise which regularities demand explanation rather than dismissal. Let's loop that back to first principles, because dark energy raises a question every student notices: why so small? If vacuum energy is just sum, the 0-point energies naive estimates overshoot by a comical factor. Symmetry is the physicist's first refuge here. Supersymmetry can cancel boson and fermion contributions, but if it's broken, as it must be, at accessible energies, an enormous residue remains. The multiverse story, wielded carefully, offers a statistical lens. If a deep theory admits a very wide distribution of vacuum energies, then observers typically measure a value near the upper boundary compatible with galaxies. Our measured value is indeed far smaller than particle physics scales, yet not wildly below the bound for structure. That's a hint, not a theorem. It only becomes predictive when paired with a concrete distribution and correlated typicalities, say linking vacuum energy with fluctuation amplitude. Until then, why so small remains a live quantitative question that keeps theory honest and observations sharp. There's a beautiful, unsettling parallel between dark energy's horizons and the black hole story we touched earlier. A true de Sitter horizon has a temperature and an entropy proportional to its area. If our fate is de Sitter-like, the number of independent states accessible to any one observer is finite. That whispers holography again. Information in gravity seems to count at boundaries. It also reminds us that forgetting is built into cosmology. As acceleration carries structures beyond reach, their detailed information is never destroyed, but is redshifted into impotence. The arrow of time is not only entropy's rise through clumping, it's a gentle loss of causal contact with most of what exists, a thinning of the cosmic library shelves as seen from one reading room. The meaning of complete explanation must live within that bounded room. If this sounds philosophical, it has a practical edge. A finite patch with a finite horizon entropy invites an operational definition of predictivity. What can even in principle be measured and inferred within this room? That question shapes how we treat the measure problem in eternal inflation, how we define typicality, and how we guard against drawing conclusions from God's eye sums over regions no observer can survey. It also motivates a new style of calculation. Translate ideas from quantum information entanglement, wedges quantum extremal surfaces into expanding spacetimes, and let them tell you how information is parceled between an observer's patch and the rest. Early results are tentative, but the direction is clear. When gravity, quantum mechanics, and thermodynamics speak together, they speak in the language of information. The observational path forward remains delightfully concrete. On the dark energy side, ever cleaner baryon acoustic oscillations across redshift to fix the distance scale. Weak lensing shear with brutal control of systematics to track growth. Redshift space distortions that read peculiar velocities as growth's time derivative. Supernova samples with better cross-calibration. Combine them and test whether geometry and growth match Einstein plus a constant vacuum. On the gravity side, cross-compare lensing and clustering to see whether light and matter respond to the same potentials. Watch for scale-dependent growth that would betray new fields or screening transitions. On the Hubble rate side, strengthen independent anchors tip of the red giant branch, masers, strong lens time delays, while testing early time fixes against nucleosynthesis and the acoustic peak phasing. On the small scale side, push dwarf galaxy kinematics, tidal streams, and strong lensing substructure to tell us whether small halos are as abundant and concentrated as cold, collisionless dark matter predict. Let 21 centimeter maps time the first light and cross-check the minimum halo masses that hosted stars. Threaded through all of this is the quietly audacious hunt for new messengers. We have photons across the spectrum and we're already fluent in their dialects. Gravitational waves are the newcomer. Nanohertz timing has likely heard a chorus of supermassive black hole binaries. Millihertz space interferometers will open the window where cosmic phase transitions, if they sang, could be heard. Ground-based detectors continue to give us a census of stellar mass compact objects. If nature is generous, we will piece together a broadband stochastic gravitational wave background with a shape that points to reheating or to a symmetry's breaking. That would be a second fossil from the first second independent of light, a corroboration or a contradiction that no rhetoric can evade. And neutrinos, quiet but implacable, continue to speak through structure. Every tightening of the mass sum from cosmology will either squeeze theory toward a single narrow range that labs can hit or reveal a tension that forces us to revisit early time assumptions. I want to return, before we draw breath, to the spirit that's threaded this whole journey. We began with a crisp, unsettling answer to why are we here? Because in a multiverse-flavoured inflationary cosmos, patches like ours will exist and observers will arise where conditions allow. That answer only earns respect when it's embedded in a scaffolding that stands up to measurement, near-scale invariance, tiny non-Gaussianity, a single clock sky, unless proven otherwise. A reionization timeline that echoes the initial spectrum. A galaxy population whose statistics match the seeds filtered through gravity, late-time distances and growth that agree or disagree in ways that point to new physics with a clear return address. Every so-so in this story is a short pause before another test, not a flourish to avoid one. And there's an ethic hiding in the method. It says, symmetry first, selection last, calculations before metaphors, cross-checks over single probes, probabilities defined where observers can stand, humility in the face of horizons. It's not austere, it's liberating. It means we can enjoy wonder without surrendering standards. The night sky can move us and move our error bars. Where next then, as an immediate human-sized step, we keep chasing the primordial tensor whisper in microwave polarization, delensing and de-dusting until either the hum emerges or the upper bounds make high hill inflation. Untenable, we map the 21 centimeter sky until the fog of the first billion years resolves into films of bubble growth we can correlate with galaxies and quasars. We weigh small-scale power with Lyman alpha forests, stellar streams and lensing arcs until warm, wavy or self-talking dark matter must either show itself or accept cold, quiet anonymity. We press the distance ladder and the early time rulers until the Hubble tension either dissolves or crystallizes into a demand for new physics. And quietly, steadily, we translate holography's grammar into cosmology so that words like horizon entropy and causal patch cash out in identities we can try to falsify. If eternal inflation is how nature writes, we are reading one page with extraordinary resolution. If it is not, the page is still ours, and its margins are wide with questions. The universe, vast and patient, has given us time to ask them. The proper thanks is to use that time well, to measure carefully, to argue cleanly, to be delighted when we're wrong, and to let the light of distant things keep teaching us how to think. Let's bring the question down another layer. Not just why does a universe like ours permit life, but why is there anything here to do the permitting Why is the cosmos made of matter at all when the equations are almost indifferent about matter and antimatter, and the early fireball could have snuffed both in a perfect draw? This is one of the most concrete, fascinating edges in the whole story, because it turns a philosophical sounding "why are we here" into a laboratory checklist. Create an imbalance, keep it through the furnace, and let it seed every atom in your body. If inflation is the overture, baryogenesis is the moment the orchestra tunes to a particular key, the key labelled more matter than antimatter. Start with the simple nightmare. In the first fractions of a second, the universe was hot enough to pour matter and antimatter out of pure energy. For every electron and anti-electron, for every quark and anti-quark. Left alone, that sea would have waited until expansion cooled it below the threshold for pair creation, and then annihilated quark with anti-quark, electron with positron, leaving behind a thin mist of photons. That is almost what happened. Almost is our good fortune. For roughly 1 billion pairs, there was one extra matter particle. When thermal annihilations ran their course, those unpaired survivors were all that remained. Every proton in you is one of those leftovers. So the first scientific version of "why are we here" is, where did the 1 in a billion excess come from? We even know the rules any answer must obey. Half a century ago, Andrei Sakharov wrote them down as 3 conditions. First, some interactions in the early universe must violate baryon number, that bookkeeping label that counts matter minus antimatter. Otherwise, you can't move the needle off 0. Second, the relevant processes must violate charge parity CP symmetry, so they prefer matter to antimatter in their rates. If everything runs equally forwards and backwards, the ledger balances. Third, the universe must have been out of equilibrium when those processes ran, because detailed balance at thermal calm wipes out any bias you try to create. These are not optional decorations, they are the minimal engine for an imbalance. Where might nature have housed that engine? One elegant idea lives close to the Standard Model's own phase transition. As the universe cooled to energies near the electroweak scale, the Higgs field took on its non-zero value and gave masses to the W and Z bosons and to quarks and leptons. If that transition had been strongly first order, if the Higgs vacuum had bubbled the way water boils, then expanding bubble walls could have provided out of equilibrium environments with CP violating interactions that create a baryon asymmetry. In the Standard Model, with the observed Higgs mass, that transition is too smooth. The boiling is more of a gentle steeping. But modest extensions, additional Higgs fields, new scalar particles can sharpen it. Electroweak baryogenesis remains an alluring testable framework because it ties the cosmic imbalance to physics we might glimpse at colliders or through precision electric dipole moment experiments. The data so far have hemmed it in but not buried it. Another route takes a detour through the neutrino sector and is, if anything, even more compelling: leptogenesis. We know from neutrino oscillation experiments that neutrinos have tiny masses. A very natural way to generate those masses is the seesaw mechanism: introduce heavy right-handed neutrinos that are their own antiparticles. The heavies decouple early decay out of equilibrium, and provided their decays violate CP, leave behind an excess of leptons over anti-leptons. Non-perturbative processes in the Standard Model plasma can then shuffle part of that lepton excess into a baryon excess. It's a beautiful two-step that uses Sakharov's conditions faithfully. Better, it connects the cosmic asymmetry to parameters we're chasing in the lab: the absolute neutrino mass scale, the mass ordering, and whether neutrinos are Majorana particles, their own antiparticles, which experiments like neutrinoless double beta decay are hunting. If that ultra-rare decay is ever seen, it won't prove leptogenesis, but it will glow a light on the path. Whichever engine ran, it had to win a series of races against the hot early universe. That furnace ran fast. Quarks and gluons locked into protons and neutrons as the temperature fell below the scale where the strong force confines them. A few minutes later, in Big Bang nuclear synthesis, those protons and neutrons fused into helium, deuterium, and a trace of lithium, while the plasma still glowed with the brightness of a small star. By the time the cosmos was a few 100,000 years old, electrons and nuclei found each other to make neutral atoms, and the microwave background photons streamed free. Through all of that, any mechanism that created an asymmetry had to avoid later processes that would erase it. The universe is a ruthless editor. It keeps only what's protected by asymmetry or frozen by expansion. This is where the Higgs field re-enters the story in a quieter, subtler way. The same field that gives particles mass also helps set the stability of our vacuum. Extrapolate the measured Higgs self-coupling and top quark mass to very high energies, and the Higgs potential might dip negative at scales far above any collider's reach. hinting that our vacuum is metastable, perched in a long-lived valley with a deeper valley beyond a distant ridge. If that's right, quantum tunneling could, in principle, end our branch of physics someday unromantically, without warning, at the speed of light. Don't panic, crude estimates give lifetimes unimaginably longer than the age of the universe. But in the early moments when inflation and reheating shook fields, violently metastability becomes a constraint. Too high an inflationary scale or too strong a coupling between the inflaton and the Higgs could have kicked the Higgs into the wrong valley. The fact we are here is a data point. Our early dynamics must have respected this precariousness. So the interplay between cosmic beginnings and particle couplings is not a metaphor. It's a boundary condition on what the inflaton and its friends were allowed to do. Step a little further along the thermal history and you arrive at a triumph that reassures us we're on the right track, Big Bang nucleosynthesis. With just the baryon to photon ratio, that precious 1 in a billion number, and the number of light neutrino species as inputs, you can calculate the primordial helium and deuterium abundances. Observations of metal-poor gas clouds and old stars match those predictions with impressive fidelity. There remains a long-standing lithium problem. Standard calculations overproduce lithium-7 relative to what we infer from the atmospheres of ancient stars. Either we have not yet mastered the messy astrophysics of lithium in stellar surfaces, or there is a small crack where new physics could slip through. That is how frontier science often looks. Almost everything hangs together, and the devil, if one is present, chooses a small decimal place as a hiding place. When atoms form and the microwave background is released, the universe becomes at last a chemistry set. Gravity continues its long work, but another gentler story begins the architecture of the periodic table. The first stars, massive and short-lived, explode and spew heavy elements into space. Successive generations forge carbon and oxygen in red giants, iron in their cores, and the really heavy elements, the gold in a ring, the iodine in a thyroid in rare violent events, neutron star mergers and some peculiar supernovae. This stellar alchemy is not incidental to why we are here. It is the means by which planets can be built and biochemistry can explore. And it's paced by numbers we've met already: the strength of gravity, the rates of nuclear reactions, the fine structure constant, the proton-electron mass ratio. Tip them and stars live shorter or longer, burn too hot or too cool, fail to make carbon or overproduce oxygen. We do not need to wave fate about. We can point to resonance energies in the carbon-producing chain and say those sit where they sit because of the symmetry-broken parameters of our low-energy world. Shift the parameters and the resonances shift. The corridor for long, generous eras of starlight is not razor-thin, but it is a corridor, not a plane. If you enjoy the way disparate pieces lock, here's a quiet lock worth admiring. The amount of ordinary matter, the baryon density, enters two independent ledgers, the deuterium abundance from nucleosynthesis, and the odd divided by even peak heights in the microwave background's acoustic spectrum. They agree. That agreement tells you that the 1 in a billion asymmetry we invoked to avoid annihilation's wipeout is the same number that counts the nuclei in your blood. It also tells you how much dark is required to make up the rest of the gravitational mass that sculpts galaxies. You can feel the method at work. Discard metaphysics, where physics can stand and keep asking for cross-checks between early-time relics and late-time maps. Now, because our theme has been honest wonder, we shouldn't skip the places where we don't yet know how to close the loop. The precise CP-violating phases available in the Standard Model's quark sector are too feeble to explain the observed baryon asymmetry by themselves, at least in the electroweak bubble picture. We need either new CP violation in the Higgs sector or the neutrino sector, or different dynamics altogether. Neutrino experiments are hard at work measuring a CP violating phase in oscillations. A large value would not directly make leptogenesis inevitable, but it would make the CP as plentiful in leptons hunch feel more grounded. Electric dipole moment searches push sensitivity to absurd levels, tightening the belt around many models of new CP violation. Collider experiments sift the Higgs interactions, looking for small deviations from standard model couplings that could hint at extra fields fuel for a stronger phase transition. The admirable thing here is not that we have a final answer, it's that the cosmos has given us multiple orthogonal handles on the same primordial question. At this point, it's fair to ask whether the multiverse flavour we've allowed into the room helps or hinders. Used lazily, it would be a way to shrug. Some bubbles got an asymmetry, some didn't. We live in one that did. Used properly, it's a demand for correlation. If the deep theory that permits many vacua also ties the size of the baryon asymmetry to, say, the neutrino mass scale, or the scale of inflation. Then you have a statistical statement. You can try to test in principal patches with larger neutrino masses may on average have different reionization histories. Patches with higher inflationary scales may be rarer if metastability bites. These are delicate speculative suggestions. We should keep them labelled as such. But the ethos is the same. Even ensemble stories must cash out in quantitative links, or they are not yet physics. All this talk of asymmetry and alchemy invites a final grounded reflection. The cosmos prefers difference over perfection. Exact symmetry, equal parts matter and antimatter, would have been sterile. Perfect smoothness, no primordial ripples, would have been dull. The universe that permits life is one that keeps breaking its own symmetries gently. The Higgs field tips the electro-weak balance. CP violation leans on matter over antimatter. Inflation smooths the big scales, but sprinkles quantum grain. The arrow of time we inhabit flows from those breaks prepared by inflation's smoothing, driven by gravity's clumping, extended by the slow burn of nuclear fusion, and written into a periodic table whose entries are the fossil record of broken symmetries in stars. Where does that leave us in our practical program with very specific next steps? Keep pushing for a detection or ever tighter bound on the primordial tensor hum in microwave polarization. It will fix the inflationary energy scale and via vacuum stability arguments inform couplings in the early universe. Keep mapping the 21 centimeter sky. The schedule of cosmic dawn is a second audit of small-scale power and of any warmth waviness or self-torque in the dark sector. Keep chasing neutrino-less double beta decay and the precise pattern of neutrino masses. If neutrinos are Majorana leptogenesis becomes loudly plausible. Keep tightening electric dipole moment searches. A discovery would shout new CP violation lives here, and model builders would have a beacon. And keep reading the Higgs with relentless attention. Small deviations in its couplings could be the fingerprints of a stronger first-order electroweak transition in a slightly bigger Higgs sector. If we succeed, the sentence "we are here because we had to be" will have been translated into a more precise paragraph: "we are here because the inflaton's fluctuations were nearly scale invariant and small, because a CP violating out of equilibrium engine tipped the matter ledger by 1 part in a billion, because the Higgs field settled into a long-lived valley whose masses make stars stable and chemistry rich, because the dark matter lets small halos form early enough, because vacuum energy is tiny and positive, because billions of years passed under a steady star on a quiet orbit. None of that is destiny, all of it is physics. And the lovely thing about physics is that it invites us to keep testing every clause. So where should we go next? We've stitched quantum seeds to galaxies, horizons to information, dark sectors to dawn, and asymmetry to atoms. There remains one last bridge that many of us cannot resist attempting, even if we must tread lightly the question of beginnings, in a truly quantum sense. No boundary proposals, tunneling stories, and whether a finite horizon, information puts a strict bound on what initial condition can mean. If time itself is emergent from entanglement and the code of a causal patch, can we make before a calculable word rather than a grammatical habit? That's a daring step, but we can take it without bravado, slowly, with the same mix of curiosity and caution that's carried us from a mottled microwave sky to a map of everything we can see. If we are to close this journey honestly, we should end where physics always ends when it has done its best, with a clear horizon, a careful to-do list, and a kind of quiet gratitude. We began with a blunt question: why are we here? And we followed it into deep water, eternal inflation and its garden of possibilities. Horizons that carry heat and count information on their skins, quantum jitters stretched to write the scaffolding of galaxies, the slow ignition of the first stars, the choreography of dark matter and the steady pressure of dark energy, the tiny, precious imbalance of matter over antimatter, the long patience of starlight that gave chemistry a billion-year calendar. Each step, when you truly look, was less an answer and more a disciplined way to keep asking the right variables, the right measurements, the right humility about what a single horizon permits us to know. So the best ending isn't to flourish, it's a steadying of the hand on the instrument. Think of what we have learned to accept as normal. That the sky's mottled afterglow is a quantum fossil, a photograph of randomness made classical by expansion and decoherence. That black holes, which once seemed the end of narratives, are ledgers that never lose the fine print, letting information leak back in correlations too subtle for clumsy calculations to see. That a universe with a tiny positive vacuum energy is not an empty finale, but a long diminuendo in which local physics keeps playing while the distant stage lights glide over the horizon. That even the shyest particles, neutrinos, leave measurable fingerprints on the growth of structure, and that the identity of the dark matter quietly sets the rhythm for dawn, for dwarfs, for disks where worlds can take their time. We have learnt to speak in two voices without contradiction. The first is the voice of symmetry of principles that narrow possibilities before we ever count observers. It is the voice that insists on consistency relations in the microwave sky, that prefers single clocks unless the data demand companions, that asks gravity to obey Einstein's rules unless growth and lensing whisper otherwise. The second is the voice of selection used sparingly and only when dynamics refuses to fix a number. It says that in a landscape of many low-energy laws, minds will find themselves in patches where stars live long and fluctuation amplitudes sit in corridors that slow the cosmic metronome to something like human tempo. The discipline is to keep those voices in order, symmetry first, selection last, and to turn both into calculations wherever possible. We have learnt too to cherish finiteness. A horizon is not a failure of nerve. It is a frame for honest inference. Cosmic variance is not a nuisance. It is the boundary law written into our error bars. The entropy of a horizon is not poetry. It is a reminder that the library of facts any one observer can even in principle assemble has a finite number of pages. Within that finitude, we have learned to be ingenious measure, new fields polarization, as well as temperature shear, as well as counts, cross-correlate, different maps to lift faint truths out of noise. Triangulate distances and growth until models either stand straighter or fall. Along the way, the cosmos asked us for courage of a very particular kind. Not swagger, but patience. The patience to sweep galactic dust out of polarization maps until a possible primordial curl pattern, if it exists at a few parts in 1,000, can be trusted. The patience to listen for a 21 centimeter whisper through a foreground 1,000,000 times brighter, and to turn that whisper into a three-dimensional film of bubbles growing in the first billion years. The patience to weigh neutrinos cosmologically, while laboratories weigh them locally, meeting in the middle without romance. The patience to map stellar streams and lensing arcs until the granularity of halos tells the truth about the dark. The patience to watch pulsar ticks and interferometer fringes until a stochastic hum from the early universe either steps forward or admits it sings too softly to be heard. If this all sounds austere, remember where it led. To a picture of time that is not a metaphysical arrow, but a practical schedule. Inflation prepared a low gravitational entropy stage and sprinkled seeds. Gravity amplified them. Plasma sang. Atoms formed. Stars lit. Metals brewed. Planets condensed. Atmospheres learned to hold their breath. Chemistry explored phase spaces it had never seen. Somewhere replication and memory stumbled into being. That stripped of flattery and fate is why we are here can be answered in the language of instruments and equations. And it is not a dry answer. It is an answer that lets you stand under a dark sky, look up at the seam of the Milky Way, and know not, guess, not insist, but know that the light has carried the story. Faithfully, quantum whispers, acoustic beats, gravitational growth, stellar, alchemy, and a long stretch of calm in which minds could learn to read. We've also learned to hold two futures lightly. In one, dark energy is truly constant. The expansion tends to a de sitter hush. Distant galaxies drift beyond conversation. Our local group merges into a single island. Stars age and thin. Even black holes on timescales that mock imagination radiate their mass away. Nothing is destroyed, everything is diluted. In the other, dark energy has texture or gravity, departs a little from Einstein on great scales. The hush is revised, perhaps softened, perhaps postponed. We do not pick the ending by taste. We read it in baryon acoustic rulers, in weak lensing maps, in redshift space distortions, in supernova light curves. And we let the numbers pick for us. That is a good way to live under a huge sky, neither to despair at distance, nor to declare victory in ignorance, but to measure. You may have noticed a thin thread of stammering in this tale, small hesitations, where the thought leans forward. It isn't effect, it's the right cadence for truth at the edge of knowledge. The universe, when we listen carefully, does not shout at us. It lets us hear one more bit of structure in a spectrum, one more correlation among distant shapes, one more coincidence that turns out not to be coincidence at all, but consequence. So we pause, we check, we move one rung up the ladder. The craft is humble because the subject is vast. If there is an ethic to take away, let it be this. Curiosity is not a luxury. It is the engine that turned a mottled microwave haze into a map of initial conditions, that turned faint radio static into a chronicle of the first stars, that weighed invisible particles with galaxies as scales, that counted information where we thought only geometry lived. And community is not sentiment, it is the tool that made the measurements honest, independent teams, failing in different ways until the only thing left was the sky's own signal. Meaning in such a world is not decreed, it is made locally under a finite horizon by minds that learned how to ask better questions than the ones they were handed. As for the multiverse, if nature writes in that spacious hand, let it be a background, not a crutch. If models that fit our patch persist in breathing out new regions elsewhere, that is a fact about the mathematics, not an invitation to stop. The right use of the idea is to compute distributions where a deep theory says parameters wander to define observer windows operationally and to test for correlated typicalities. The wrong use is to file every awkward number under somewhere. That is the distinction between an ending that closes curiosity and an ending that opens a door quietly and lets fresh air in. So here we are, near our own horizon, not the cosmic one, but the horizon of a single conversation. We have walked from quantum ripples to reionization films, from dwarf galaxy cores to horizon entropy, from baryon asymmetry to biosignature dreams, from neutrino mass sums to lensing shears, from the hum of merging black holes to the hoped-for murmur of inflation's tensors. We have, I hope, earned one precise sentence: we are here not because the universe was obliged to make us, but because the numbers that describe our patch make long computations possible. Those numbers measured, not wished, left time for stars to be generous and for curiosity to become method. What remains is beautiful in its ordinariness. We go on building the instruments. We go on tightening the systematics until disagreements grow sharp enough to be instructive or soft enough to let coherence shine. We treat every null result as a narrowing of the path ahead, every anomaly as a question with a return address, every surprise as a chance to learn a better grammar for the world. We keep one eye on horizons and the other on the data table. We accept that forgetting is part of physics in a universe with acceleration, and we trade that melancholy for the privilege of knowing anything at all with confidence. If you want a final image to carry out of the room, take this one, a small quiet telescope cooling in the dark, its detectors a breath above absolute zero, waiting to feel a curl in the oldest light that would tell us the height of a hill the universe once descended, or a forest of radio antennas listening for a dip in the sky's spectrum that marks the first stars turning the hydrogen fog into a landscape of bubbles, or a cavern under a mountain where a crystal waits for the softest tap that could mean the dark has finally said hello. These are not grand gestures, they are acts of attention. The world has always rewarded attention, and that is where I'll leave it. Not with a proclamation, but with an invitation to keep walking outward until the next horizon, to keep letting wonder, set the questions and evidence, decide the answers, to let the small stammers of honest thought be the rhythm under a sky so large that even our best mathematics feels like a kind of reverence. So thank you for listening, for thinking, for holding both awe and care in the same hand. The universe will take it from here.